Fascinating Ice Age facts. Tonight, we journey back into a world locked in ice, an era when mammoths wandered the plains. Saber-tooths stalked their prey, and ice itself sculpted the face of the earth. Before we go any further, we would love to hear where in the world you are watching from, and what time it is for you at this very moment. Share it with us in the comments below, then make yourself comfortable and prepare for a calm and gentle voyage. An ice age is a long-lasting chapter in Earth's story, defined by widespread global cooling, during which enormous ice sheets spread across great expanses of the continents. Unlike an ordinary winter or a brief seasonal chill, which lasts only months and affects limited areas, an ice age unfolds over thousands or even millions of years, reshaping the planet's climate landscapes and living systems at a fundamental level. Throughout these vast stretches of time, average global temperatures fall significantly, enabling ice to build far beyond the poles, pushing into the mid-latitudes and leaving deep, lasting marks on the land. The crucial difference between an ice age and everyday cold periods lies in both its immense scale and its extraordinary length. Seasonal winters are brief chapters shaped by the rhythm of Earth's orbit and its axial tilt, producing the familiar annual pattern of cold and warmth. Ice ages, by contrast, are defined on prolonged global cooling, during which immense ice sheets endure for thousands of years, occasionally interrupted by warmer intervals, called interglacials. These interglacial periods temporarily shrink the reach of ice, yet the broader cycle of glacial advance and retreat remains the hallmark of an ice age. The forces that drive ice ages are intricate and interconnected, involving changes in Earth's orbit known as Milankovitch cycles, which affect how sunlight is distributed across the planet. Over long spans of time, these subtle shifts slowly reshape climate patterns, allowing ice sheets to expand or withdraw. Additional influences, including the composition of the atmosphere, volcanic eruptions, and the movement of ocean currents, also play vital roles in triggering and ending glacial phases. Grasping the difference between an ice age and ordinary seasonal cold helps reveal the vast scale of Earth's climate system. A winter may blanket a region with snow and frost, but an ice age redraws entire continents, forming new landscapes and guiding the course of life's evolution over thousands of years. Appreciating these contrasts highlights why exploring Earth's climatic past is so important for understanding the powerful forces that have shaped the planet's surface. As we turn our attention to the timeline of the most recent ice age, it becomes important to consider when these enormous climatic changes took place and which key periods define their development. When did the most recent ice age begin, and what major timeframes mark its history? The latest ice age, commonly known as the Quaternary glaciation, started about 258 million years ago and continues into the present, though it has passed through many phases of advance and retreat during this long interval. This era ushered in a sequence of glacial and interglacial stages that profoundly molded Earth's surface and climate record. The course of this continuing ice age is marked by notable fluctuations, with the most recent major glacial phase, called the last glacial maximum, reaching its height roughly 20,000 years ago. At that time, enormous ice sheets covered large areas of North America, Northern Europe, and Asia, dramatically altering landscapes and ecosystems alike. The shift from glacial conditions to interglacial phases is defined by intricate changes in climate driven by variations in Earth's orbit. Axial tilt and precession together referred to as cycles. These changes affect how solar energy is distributed and how intense it is at Earth's surface, triggering repeating patterns of cooling and warming. The conclusion of the last glacial period around 11,700 years ago brought about the present interglacial phase known as the Holocene, which has offered relatively stable climate conditions that supported the rise of human societies and civilizations. Across this long timeline, the transitions between glacial and interglacial stages are marked by major environmental changes. Expansions of ice sheets, fluctuations in sea level, and transformations in plant and animal life are defining features of these cycles. Glacial phases are characterized by the widespread growth of ice sheets, which lowers sea levels as enormous quantities of water become trapped in ice. In contrast, interglacial periods are marked by the retreat of ice sheets, higher sea levels, and warmer average global temperatures. These alternating stages have played a crucial role in shaping Earth's surface, influencing ocean circulation, and driving evolutionary changes among living organisms. Understanding these major timeframes helps place the dynamic nature of Earth's climate system into context. As scientists refine the timing and sequence of these cycles, they uncover not only details of Earth's climatic past, but also insights into the processes that continue to influence today's climate. Examining the main characteristics that define an ice age allows us to recognize the profound environmental changes that have taken place over millions of years, laying the groundwork for a deeper understanding of the climatic and environmental signatures that set these periods apart. At the core of an ice age is a distinctive climate defined by persistent and widespread cooling. Such intervals are marked by a notable decline in global temperatures, often several degrees Celsius, lower than during interglacial phases, leading to the expansion of continental ice sheets across vast areas. This prolonged cooling results from complex interactions between Earth's orbit axial tilt and incoming solar radiation factors, collectively known as Milankovitch cycles, which regulate how much sunlight reaches different regions of the planet. These repeating variations create conditions that sustain long-lasting cold phases, extending from tens of thousands to hundreds of thousands of years. Environmental conditions during an ice age are equally distinctive. Lower temperatures cause polar ice sheets to grow and spread far beyond their usual boundaries, covering large areas of North America, Eurasia, and other high-latitude regions. This expansion increases Earth's albedo or reflectivity, sending more sunlight back into space and further strengthening the cooling trend. At the same time, glaciers become thicker and more extensive, carving deep valleys and reshaping the terrain through continuous erosion. The colder climate also reduces vegetation in many regions, turning once fertile landscapes into tundra or desert-like environments where ecosystems must adapt to harsh conditions and limited resources. Patterns of precipitation also change dramatically, with some regions receiving heavier snowfall that feeds the ice sheets, while others become progressively drier. The combined effects of colder temperatures and altered precipitation produce landscapes dominated by ice, featuring landforms such as deep fjords, U-shaped valleys, and moraines. Moraine deposits trace the former edges of retreating glaciers. Recognizing these climatic and environmental signatures offers vital insight into the nature of ice ages. They provide the essential framework for studying the remains of these cold periods preserved in Earth's geological record, enabling scientists to reconstruct the history of past climate changes. This close relationship between climate environment and physical landscapes underpins the study of how researchers interpret Earth's glacial history through geological evidence. To reveal the story of Earth's ice ages, scientists depend on a wide range of evidence that serves as a quiet archive imprinted on the planet's surface. One of the most important tools in this effort is the examination of glacial deposits, extensive layers of till gravel and layered sediments left behind as glaciers advance and retreat. These materials, commonly found in moraines and outwash plains, act as clear indicators of former glacial activity. By studying their composition, distribution, and layering, scientists can reconstruct the extent and timing of ice sheet expansion across thousands of years. Another important line of evidence emerges from studying landforms such as U-shaped valleys, fjords, and drumlins, all of which bear the unmistakable marks of glacial erosion. These landscapes record the direction and strength of ice movement, offering valuable clues about how extensive glaciers were and how much ice existed during different eras. Scientists also examine the spread of erratics, large rocks carried by glaciers far from their original bedrock locations, which helps reveal the routes glaciers followed and the dynamics of their flow. Beyond what is visible at the surface, sediments preserved in lakes and oceans provide an even richer archive of information. Core samples taken from these settings contain layered deposits that accumulated gradually over time, including pollen grains, volcanic ash, and distinctive isotopic signals. Isotope analysis, especially of oxygen. Isotopes found in glacial ice and marine sediments allows researchers such as to reconstruct changes in global temperature and total ice volume. These isotope ratios shift in step with the advance and retreat of ice sheets, acting as an exceptionally reliable timekeeper for glacial cycles. Fossil evidence further strengthens this picture as changes in the distribution of plants and animals mirror the climatic shifts linked to glaciation. When these records are combined with radiometric dating methods, such as carbon dating of organic remains or uranium series dating of minerals, scientists can build a detailed and accurate timeline of past ice ages. By bringing together geological, chemical, and biological evidence, researchers reconstruct Earth's frozen history, uncovering long-term climate patterns that have shaped the planet's surface across countless millennia. This integrated approach forms the basis for understanding the complex back and forth between glacial and interglacial phases within an ice age. Within the wider structure of an ice age, glacial and interglacial periods represent clearly different climate states produced by intricate interactions between Earth's orbit, the composition of the atmosphere, and ocean circulation. During glacial periods, enormous ice sheets spread far beyond their usual limits, covering large areas of North America, Europe, and Asia. These ice masses can reach hundreds of meters in thickness, dramatically reshaping the terrain beneath them. Climate conditions during such times become significantly colder, often by several degrees Celsius, as expanding ice reflects more incoming sunlight, reinforcing cooling through a process known as the albedo effect. The widespread presence of ice also disrupts the movement of moisture, reducing precipitation in some regions and helping maintain the continued growth of ice sheets. By contrast, interglacial periods are warmer intervals that follow the height of glaciation. During these phases, ice sheets retreat substantially, revealing land that had long been buried beneath ice. Global temperatures rise often by 4 to 8 degrees Celsius compared to glacial conditions, creating environments more favorable for forests, grasslands, and a wide range of ecosystems. As ice melts, during interglacials, water previously locked in glaciers returns to the oceans, raising sea levels sometimes by as much as 120 meters relative to glacial maxima. This rise inundates coastal plains and reshapes continental edges, forming new habitats and altering patterns of ocean circulation. The shift between glacial and interglacial states is driven by subtle changes in Earth's orbital characteristics, called Milankovitch cycles, which control how solar energy is distributed across the planet. Variations in greenhouse gases, particularly carbon dioxide and methane, further influence the climate response, intensifying cooling during glacial phases or enhancing warming during interglacials. These repeating cycles, spanning tens of thousands to hundreds of thousands of years, have defined Earth's climatic past and guided the evolution of its biosphere. Recognizing the differences between glacial and interglacial periods highlights how sensitive Earth's climate system is to a wide range of internal and external influences. This ongoing interaction not only shapes land environments but also prepares the ground for broader impacts on global climate patterns and sea levels, which are examined next. Ice ages have a deep and lasting impact on global climate patterns and sea levels, transforming Earth's environment over tens of thousands to millions of years. During these times, massive ice sheets and glaciers spread across continents, greatly increasing Earth's albedo, a measure of how much sunlight the surface reflects. As ice blankets vast areas, more solar energy is bounced back into space, reinforcing a cooling feedback loop that sustains and intensifies cold conditions. This heightened reflectivity does more than simply cool specific regions. It also alters atmospheric circulation, interrupting familiar weather patterns and driving shifts in climate zones across the planet. The spread of ice sheets has a profound effect on sea levels as well. When enormous volumes of water become locked within vast glaciers, and ice sheets' global sea levels fall sometimes by more than 100 meters at the height of the last glacial maximum. Such declines uncover continental shelves, forming land bridges that reshape migration pathways for humans and animals alike and modify ocean circulation. In contrast, during interglacial phases, periods characterized by relative warmth, these large ice bodies are put to shrink, releasing their stored water back into the oceans and causing sea levels to rise once more. This repeating cycle of glaciation and deglaciation produces major transformations in coastal settings, ecosystems, and the overall stability of the global climate. As ice and water are redistributed, both oceanic and atmospheric circulation are affected, which then influences weather systems and climate variability worldwide. For example, the influx of fresh water from melting ice can weaken or reroute major ocean currents, such as the Gulf Stream, resulting in episodes of regional cooling or warming. Together, these linked processes generate a highly dynamic climate system that moves between cold and warm states, shaping Earth's environmental past. Exploring how ice ages affect climate and sea levels reveals only one part of a much larger and more complex picture. To understand this system fully, it is necessary to examine what governs the timing and strength of these glacial cycles, particularly the subtle yet influential changes in Earth's orbital characteristics. What part do variations in Earth's orbit play in determining when ice ages occur and how intense they become? Earth's orbital variations are central to controlling the timing and magnitude of ice ages operating through a repeating process known as Milankovitch cycles. These small but persistent alterations in the planet's motion affect how sunlight is distributed and how intense it is across different regions of Earth, laying the groundwork for glacial and interglacial phases over spans ranging from tens of thousands to hundreds of thousands of years. Three main elements define these orbital variations. First, the eccentricity of Earth's orbit changes roughly every 100,000 years, shifting the orbit between a more circular and a more elliptical shape. When the orbit becomes more elongated, the contrast between Earth's nearest point to the Sun and its most distant point grows, influencing seasonal differences. Second, axial tilt, also called obliquity, varies on a cycle of about 40 or 1,000 years, altering the angle of Earth's axis relative to its orbital plane. A greater tilt intensifies seasonal contrasts, producing warmer summers and colder winters conditions that can either encourage ice sheet expansion or promote melting, depending on the timing. Third, the precession of Earth's axis, occurring over approximately 23,000 years. Shifts when seasons occur relative to Earth's position along its orbit, further adjusting patterns of seasonal and latitudinal insolation. These orbital inflow superverscences do not operate independently. Instead, they interact to generate complex patterns of insolation, the solar energy received at different latitudes and seasons. When these combined conditions result in cooler summers in the northern hemisphere, ice sheets are more likely to grow, triggering or strengthening an ice age. Conversely, times of increased insolation in these regions tend to encourage melting and the onset of interglacial warmth. The interaction of these cycles helps explain why ice ages have followed rhythmic and relatively predictable patterns throughout Earth's history. Gaining insight into how Earth's orbital variations coordinate these glacial cycles highlights the delicate balance that governs the planet's climate system. Recognizing these natural rhythms offers essential understanding of the processes that have shaped Earth's climate over thousands of years, and provides a critical foundation for examining the modern climate changes we face today. The study of ice ages goes beyond simple curiosity about Earth's remote past. It offers crucial perspective for understanding the complexity of present-day climate change. The repeating nature of ice ages demonstrates that Earth's climate system is highly sensitive to a network of interacting factors, many of which are still active. By investigating the mechanisms that initiated and ended past glacial periods, scientists gain valuable tools for interpreting current climate variability and anticipating future developments. For example, the dramatic swings in global temperature and ice coverage during ice ages reveal how rapidly climate can shift, underscoring that today's warming exists within a broader dynamic system rather than as an isolated event. Insights drawn from Ice Age research highlight the critical role of feedback mechanisms in regulating climate. During glacial phases, expanding ice and snow surfaces reflect a greater portion of incoming sunlight, strengthening cooling through a process known as albedo feedback. In contrast, during interglacial intervals, shrinking ice cover allows more solar energy to be absorbed, intensifying warming. Understanding how these feedback processes have functioned throughout Earth's past enables scientists to better anticipate how present-day changes driven by greenhouse gas emissions might provoke similar or opposing reactions. This perspective also reveals the finely tuned balance within Earth's climate system and shows how even subtle shifts can lead to far-reaching consequences. In addition, recognizing the natural variability embedded within Ice Age cycles improves our capacity to separate human-driven impacts from natural climate fluctuations. This distinction is essential for shaping effective policies and mitigation strategies. As ice ages are controlled by intricate interactions among Earth's orbit, solar radiation, atmospheric composition, and ocean currents. Examining their triggers and transitions provides a valuable framework for identifying early warning signs of climate tipping points today. In this way, the study of ice ages serves as a mirror reflecting both the resilience and the vulnerabilities of Earth's climate. It helps us grasp the scale of natural climate variability and reinforces the importance of responsible stewardship of our planet. As we move through a period of rapid climate change, lessons from Earth's frozen history become indispensable guides, reminding us that climate systems are at once highly dynamic and deeply interconnected. Earth's climate history is closely linked to the rhythms of the cosmos. The most powerful drivers of long-term climate change are astronomical factors that slowly yet steadily alter Earth's position in relation to the Sun. These celestial influences are governed primarily by three key parameters: the eccentricity of Earth's orbit, the tilt or obliquity of its axis, and the precession of the equinoxes. Together, these components form what are called Milankovitch cycles, operating over timescales that range from tens of thousands to hundreds of thousands of years. Eccentricity describes how stretched Earth's orbit is around the Sun. When the orbit becomes more elliptical, the distance between Earth and the Sun changes noticeably throughout the year, affecting the intensity of solar radiation the planet receives. These variations influence seasonal contrasts that are crucial in triggering glacial and interglacial periods. Although changes in eccentricity occur relatively slowly over roughly 100,000-year cycles, their climatic impact can be significant when combined with other orbital variations. The tilt of Earth's axis, known as obliquity, shifts between about 22.1 and 24.5 degrees over approximately 41,000 years. Variations in axial tilt alter the strength of the seasons. Larger tilt angles intensify seasonal extremes, which can promote more extensive ice sheet growth during colder intervals. By contrast, a smaller tilt tends to soften seasonal differences, supporting ice melt and a warmer global climate. Precession, the slow wobble of Earth's rotational axis, unfolds over around 26,000 years. This wobble changes the timing of the seasons relative to Earth's position along its orbit, affecting how solar energy is distributed between the hemispheres. When combined with eccentricity and obliquity, precession can either heighten or reduce seasonal contrasts, making it a key contributor to the progression of Ice Age cycles. These orbital variations do not act independently. Instead, their repeating interaction controls solar insolation, the amount of solar energy reaching Earth's surface across immense spans of time. This complex interplay of celestial mechanics underlies both the timing and the intensity of ice ages, establishing the broad rhythm of Earth's climate. Understanding these cycles shows how astronomical forces act as slow yet persistent drivers of our planet's climatic trajectory. Milankovitch cycles provide the fundamental beat behind Earth's long-term climate variability, coordinating the rise and fall of Ice Age cycles through gradual changes in orbital parameters. These cycles involve shifts in Earth's eccentricity, axial tilt, and precession, each functioning on its own timescale from roughly 41,000 to 100,000 years, and together shaping how solar radiation is distributed across latitudes and seasons. Eccentricity, which defines the shape of Earth's orbit around the Sun, ranges from nearly circular to more elliptical, influencing the total amount of solar energy the planet receives. When Earth's orbit becomes more elongated, the contrast in solar insolation between perihelion and aphelion grows stronger, sharpening seasonal differences, particularly at high latitudes. Axial tilt, which fluctuates between about 22.1 degree and 24.5 degree, governs how intense the seasons become. A greater tilt heightens seasonal extremes, producing warmer summers and colder winters, while a smaller tilt generally results in milder, more even conditions. The slow wobble of Earth's rotational axis also influences the timing of solstices and equinoxes in relation to Earth's orbit, reshaping how seasonal contrasts are distributed between the hemispheres. Together, these interacting cycles generate a complex pattern of climate variability that unfolds over tens of thousands to hundreds of thousands of years. When the combined influences of eccentricity, tilt, and precession align in a way that reduces summer insolation at high northern latitudes, especially during the boreal summer ice sheets are able to expand, setting glaciations in motion. In contrast, times when summer insolation increases promote the melting of ice sheets, marking the close of glacial periods. These orbital variations alone, however, do not fully explain the emergence of ice ages. Instead, they prepare the conditions by regulating how much solar energy reaches Earth's surface. Additional feedback processes, particularly shifts in atmospheric composition, play crucial roles in strengthening or weakening the climate's response. This intricate interaction between orbital mechanics and atmospheric influences forms the foundation of Earth's repeating ice age cycles and opens the way to understanding how greenhouse gases shape the advance and retreat of these massive ice sheets. Greenhouse gases, most notably carbon dioxide and methane, act as central regulators within Earth's climate system, exerting a powerful influence on both the beginning and the end of ice ages. Their function goes far beyond serving as simple indicators of climate change, as they actively participate in feedback loops that either amplify or moderate temperature shifts. During glacial periods, global temperatures fall and vast ice sheets spread. Yet the scale and persistence of these cold phases are closely tied to the concentration of greenhouse gases in the atmosphere. As ice sheets expand, they increase Earth's albedo, reflecting a greater portion of incoming solar radiation and reinforcing cooling. At the same time, colder conditions often coincide with reduced CO2 levels, as cooler oceans alter gas exchange and changes in biological activity further lower greenhouse gas concentrations. This combination creates a self-reinforcing cycle that helps maintain glacial conditions. By contrast, the conclusion of an ice age depends on the gradual buildup of greenhouse gases, which more effectively trap outgoing infrared radiation, slowly warming the planet and encouraging ice sheets to retreat. Natural fluctuations in greenhouse gas levels arise from a blend of physical, biological, and geological processes, including variations in ocean circulation shifts in vegetation cover and episodes of volcanic activity. The interaction among these factors determines the pace at which Earth moves from glacial to interglacial states. It is important to recognize that while orbital changes primarily initiate ice age cycles, greenhouse gases serve as amplifiers that control their intensity and duration. Their atmospheric concentrations can either deepen cooling or accelerate warming, effectively functioning as internal regulators of the climate system. This dynamic highlights the significance of greenhouse gases, not only in Earth's distant past, but also in present-day climate discussions, as human actions now disrupt their natural balance with far-reaching consequences for future climate stability. Building on this perspective, it becomes necessary to examine other natural forces that shape Earth's climate during these cycles, including volcanic activity and aerosols, which can briefly interrupt or strengthen climate trends driven by greenhouse gases. Volcanic activity and aerosols play an important role in influencing Earth's climate throughout ice age cycles by altering the planet's energy balance and atmospheric makeup. When volcanoes erupt, they inject large amounts of ash, sulfur dioxide, and other particles into the stratosphere. These aerosols possess reflective qualities, scattering incoming sunlight and temporarily decreasing the amount of solar energy that reaches Earth's surface. This process, commonly referred to as volcanic cooling, can cause short-term drops in global temperature and may trigger or intensify glacial conditions if eruptions coincide with particularly sensitive phases of the climate cycle. The effects of aerosols are not limited to immediate cooling, as sulfate aerosols in particular can remain suspended in the atmosphere for months or even years, sustaining a reflective layer that helps maintain lower global temperatures over extended periods. During transitions adult between ice ages, heightened volcanic activity can help sustain extended cooling phases by strengthening the accumulation of snow and ice as volcanic aerosols reduce the incoming warmth that would normally limit glacial expansion. In contrast, when major eruptions subside, aerosol levels in the atmosphere slowly decline, allowing temperatures to rise again, and in some cases bringing glacial periods to an end. The effect of volcanic aerosols does not act in isolation. Instead, it weaves closely together with other climate drivers, including greenhouse gas concentrations and variations in Earth's orbit. For example, times of intensified volcanic activity often align with natural cooling cycles, driven by orbital changes, intensifying the impact of reduced insolation associated with certain orbital configurations. This combination can hasten the onset of glacial periods, highlighting the intricate feedback processes that regulate Earth's climate system. Gaining insight into how volcanic aerosols influence ice age dynamics emphasizes the significance of temporary external forces in shaping long-term climate trends. While changes in orbit and atmospheric composition establish the broader conditions, episodic volcanic events can function as triggers, pushing the climate toward either glacial or interglacial states. Acknowledging these relationships deepens our understanding of the complexity of Earth's climate and the fragile balance it has maintained over thousands of years. As we continue exploring the mechanisms behind ice age cycles, it becomes clear that ocean currents and the movement of heat are equally essential in regulating the planet's climatic rhythms. Their impact on both regional and global temperature patterns forms a compelling chapter in the narrative of Earth's icy past. These immense conveyor-like systems redistribute heat around the globe, with surface currents carrying warm water from equatorial regions toward higher latitudes. At the same time, deep ocean currents transport colder water back toward the equator, and this delicate circulation strongly influences regional climates, often determining whether conditions favor glaciation or interglacial phases. During ice ages, changes in the routes of ocean currents can greatly intensify cooling in polar areas. For instance, shifts in the strength or direction of major currents, such as the Gulf Stream or the thermohaline circulation, can restrict the flow of warm water toward higher latitudes. When the thermohaline system weakens or becomes disrupted, less heat reaches the poles, accelerating the growth of ice sheets. Conversely, adjustments that allow more heat to move poleward can reduce glaciation, temporarily slowing or interrupting the advance of an ice age. The way heat is distributed by ocean currents is closely tied to the arrangement of continents and the shape of the seafloor. During ice ages, lower sea levels expose continental shelves and redirect current pathways, often reinforcing cooling trends. These changes can generate feedback loops. For example, expanding ice sheets raise Earth's albedo, reflecting more sunlight and driving further cooling. This additional cooling promotes the spread of polar sea ice, which acts as an insulating layer, limiting heat exchange between the ocean and the atmosphere and sustaining cold conditions. Furthermore, cooler ocean surfaces during ice ages influence the amount of moisture the atmosphere can hold, leading to shifts in precipitation patterns that may either encourage ice sheet expansion or support regional warming through increased cloud cover. The intricate relationship between ocean currents and heat transport highlights their critical role in initiating and maintaining glacial cycles. Even minor changes in these ocean pathways, whether driven by tectonic movements or orbital variations, can cascade into major climate shifts, setting the rhythm for the advance and retreat of ice ages. The role of ocean currents extends beyond simply moving heat. They also help establish feedback processes that can either amplify or moderate climate variability during glacial periods. Feedback mechanisms are central to determining the strength and duration of climate changes during ice ages, acting as either enhancers or stabilizers of initial shifts. These processes arise from complex interactions within Earth's climate system and often form feedback loops that intensify or soften temperature changes. One of the most important amplifying processes is the albedo effect, in which the spread of ice sheets increases, Earth's reflectivity reducing the amount of solar energy absorbed. As ice expands, more sunlight is reflected back into space, leading to additional cooling and further ice growth. In contrast, when ice retreats, darker land or ocean surfaces are revealed, absorbing more heat and encouraging warming. This negative feedback helps slow rapid drops in temperature. Atmospheric greenhouse gases, particularly carbon dioxide and methane, act as key regulators within these feedback systems. During cooler intervals, falling temperatures can cause greenhouse gases to become trapped within expanding ice sheets and ocean sediments, lowering their levels in the atmosphere and strengthening ongoing cooling trends. In contrast, warmer phases frequently lead to the release of these gases from natural storage reservoirs, increasing their atmospheric presence, intensifying the greenhouse effect, and speeding up temperature increases. These shifting exchanges establish a sensitive balance that shapes both the advance and the withdrawal of glacial periods. Vegetation cover also plays an active role in climate feedback processes. As ice sheets expand, they reduce land-based plant life, which weakens the planet's ability to sequester carbon. With less vegetation available, the removal of CO2 from the atmosphere declines further, reinforcing cooling conditions. Conversely, when glaciers retreat, increased plant growth can draw down atmospheric CO2, helping to moderate warming. Ocean-related feedbacks, including changes in thermohaline circulation, affect how heat and carbon are distributed throughout the climate system. During ice ages, shifts in ocean currents may strengthen cooling by spreading cold deep waters, or soften it by transporting more heat from equatorial regions. Together, these interacting feedbacks coordinate the advance and retreat of Earth's glacial cycles, illustrating how tightly linked processes can either amplify or dampen climate changes over thousands of years. Gaining insight into these mechanisms offers valuable understanding of the complex rhythm of Earth's climate system during some of its most extreme phases. The positioning of Earth's continents and the arrangement of land masses play a crucial role in directing the planet's climate cycles, especially during ice ages. Across geological time, the movement of continents driven by plate tectonics reshapes oceanic and atmospheric circulation patterns, which in turn influence overall climate stability. When continents lie closer to the poles, they can encourage the growth and long-term survival of ice sheets by providing broad, land-based surfaces where snow can accumulate as observed during earlier glacial periods. When land masses are located nearer the equator, they tend to support warmer, more tropical conditions, lowering the chances of large ice sheets forming. The configuration of continents also affects ocean currents, which are essential for redistributing heat around the globe. For instance, the opening or closing of ocean passages, such as connections between the Atlantic and Pacific, can significantly alter pathways of heat transport. During certain ice ages, the emergence of major land barriers, like the Isthmus of Panama, redirected ocean circulation, increasing the flow of cold water into northern latitudes and promoting cooler conditions that helped maintain ice sheets. In addition, large landmasses at high latitudes can influence atmospheric circulation by altering jet streams and storm tracks. These adjustments can lead to prolonged periods of colder weather over continents, aiding the expansion of glaciers. Continental arrangements also govern the balance between land and sea, affecting Earth's albedo or reflectivity. Widespread ice cover across polar land areas raises the planet's reflectivity, reducing heat absorption and strengthening cooling trends. Throughout Earth's history, the shifting positions of continents have at times aligned with orbital variations, producing the repeating pattern of ice ages. As land masses moved, they reshaped routes for heat and moisture, transport setting conditions for the growth and decline of ice sheets. Over millions of years, these large-scale tectonic changes have interacted with other climate influences, forming intricate feedback systems that drive long-term climate oscillations. This complex interplay between continents and ocean currents highlights the powerful role landmass configuration plays within Earth's climate system. As we continue to explore, further questions naturally emerge. Could influences beyond Earth itself also play a meaningful role in these natural cycles, potentially helping to trigger ice ages in addition to processes occurring within the atmosphere and oceans? External extraterrestrial influences have long been recognized as important factors shaping Earth's climate across geological timescales. Among the most significant are changes in Earth's orbital characteristics, collectively called Milankovitch cycles, which are considered key drivers of long-term climate change, including the initiation and retreat of ice ages. These cycles involve gradual variations in the shape of Earth's orbit, known as eccentricity, the tilt of its axis, called obliquity, and the slow wobble of that axis, referred to as precession. Each of these changes alters how solar radiation is distributed and how intense it is across different regions of the planet, slowly guiding Earth's climate toward colder or warmer conditions. The eccentricity of Earth's orbit shifts over cycles of roughly 100,000 and 400,000 years, changing the distance between our planet and the Sun. When the orbit grows more elongated, the contrast between seasons becomes stronger, often leading to cooler summers in the northern hemisphere, conditions that favor the growth of ice sheets. Changes in axial tilt affect how intense the seasons become, with a greater tilt increasing seasonal extremes and a smaller tilt encouraging more even temperatures throughout the year. Precession, the gentle wobble of Earth's axis controls the timing of the seasons in relation to Earth's position along its orbit, further shaping seasonal climate patterns. These orbital changes do not act independently. Together, they influence how much solar energy reaches Earth's surface, especially at high latitudes where ice sheets are particularly sensitive. During times when these factors combine to reduce summer insolation in the northern hemisphere, snow and ice are more likely to survive year-round, slowly building up into glaciers. Across thousands of years, this steady accumulation can spread into immense ice sheets that blanket large areas of the continents, marking the onset of an ice age. The interaction between cosmic influences and Earth's internal climate systems highlights the complexity of ice age cycles. Acknowledging the importance of extraterrestrial forces deepens our understanding of how external factors can disturb the delicate balance of Earth's climate, paving the way for the dramatic glacial episodes that have shaped our planet's past. With this groundwork in place, we now turn to consider what glaciers are and how they develop during these frozen eras. Glaciers rank among the most remarkable features of Ice Age landscapes, representing the immense force of ice accumulated over long periods. They are vast, slow-moving streams of ice formed from compressed snow, which gradually turns into dense, crystalline ice under constant pressure. Unlike seasonal snowfall glaciers, emerge through an extended process in which snowfall consistently exceeds melting and sublimation over many years, resulting in continuous buildup. This process begins in regions where the climate remains cold enough to prevent complete melting, most often at high latitudes or elevated terrain. As layers of snow grow thicker, their weight compresses the lower layers, forcing out air pockets and increasing density. Over decades or even centuries, these layers fuse into solid ice. This transformation is gradual rather than sudden, driven by the combined influences of gravity, pressure, and temperature. Once a critical mass is achieved, the ice starts to move slowly outward and downhill, carving valleys and reshaping the land beneath it. The formation of glaciers is closely tied to the climatic conditions of the Ice Age. Lower global temperatures meant that snow lingered longer, each year allowing glaciers to expand in size and reach. As snowfall continued without significant interruption, glaciers increased both in thickness and in horizontal spread, often joining together into larger ice bodies. These growing glaciers could extend across enormous regions, sometimes covering hundreds of thousands of square kilometers. The behavior of glacier growth depends on a fine balance between surface accumulation and melting or sublimation at the margins. When accumulation outweighs loss, the glacier advances, pushing into new areas. When melting exceeds snowfall, the glacier retreats. During ice ages, long-lasting cold conditions shifted this balance toward growth, resulting in the creation of massive ice sheets that covered much of the continents. Understanding how glaciers form in these frigid periods helps clarify the mechanisms behind their expansion and movement. It also prepares us to examine larger-scale processes, explaining how these ice masses develop into powerful ice sheets such as the Laurentide and Eurasian sheets, which profoundly altered Earth's surface during the Ice Age. The expansion and growth of large ice sheets like the Laurentide and Eurasian sheets arise from a complex interaction of climatic, topographic, and oceanic influences. During phases of pronounced cooling, usually linked to glacial maxima, increased snowfall begins to gather over broad land areas. This accumulation exceeds the amount of ice lost during warmer seasons, producing a net gain in ice volume. Over time, this ongoing buildup causes the ice sheet to spread outward, filling valleys and covering vast portions of the continent. The formation of an ice sheet depends on a careful balance between accumulation and ablation. Snowfall, often supplied by colder temperatures and greater moisture carried by polar or westerly winds, lays down layers of snow that are gradually compressed into dense ice by the weight of layers above. This mechanism, known as fernification, gradually converts loose, granular snow into dense, solid ice over periods spanning decades or even centuries. As layers of ice accumulate and thicken, pressure at the base steadily rises, forcing the ice to spread outward. Under its own mass, its movement guided and constrained by the shape of the land beneath. Gravity serves as the primary driving force, allowing the ice to slide, bend, and slowly creep forward, carving into landscapes and extending its reach across vast areas. Variations in climate are crucial during phases of expansion. Colder intervals, such as ice ages, are marked by global temperature declines that greatly reduce melting. At the same time, shifts in sea levels and ocean circulation can alter how much moisture reaches the edges of ice sheets, supplying additional snowfall that promotes further growth. The ultimate size of these ice sheets is also influenced by the availability of moisture sources, the contours of the land, and the presence of ice-dividing mountain ranges that channel snowfall into particular regions. The Laurentide ice sheet, for instance, expanded dramatically during the last glacial period, spreading across much of North America as a result of lower temperatures combined with heavier snowfall in northern latitudes. In a similar way, the Eurasian ice sheet developed through widespread snowfall over northern Europe and Siberia, strengthened by persistent cold Arctic air masses. This cycle of accumulation and outward growth reflects the dynamic interaction between climate geography and atmospheric circulation. As these enormous ice sheets expanded, they not only molded Earth's surface, but also exerted a powerful influence on global climate patterns and sea levels throughout the Ice Age era. Building on this understanding, it becomes important to clearly distinguish between different supercontinental types of ice masses. How do ice sheets differ from ice caps and glaciers? Although glaciers, ice caps and ice sheets are all massive accumulations of ice, they vary significantly in scale, setting, and their effects on the landscape. Recognizing these differences is essential for understanding how each shapes Earth's surface in its own way. Ice sheets are the largest of the three, spreading across thousands of square kilometers and containing immense volumes of ice mainly found in Greenland and Antarctica. These vast bodies often extend beyond individual land boundaries, covering entire continental regions, and their tremendous weight and movement enable them to reshape landscapes on a continental scale. Because of their size, they can alter global sea levels and influence climate systems worldwide, making them key components of Earth's climate balance. Ice caps, by comparison, are smaller but still substantial, typically located at high elevations or in polar environments. They form dome-shaped masses that cover mountainous regions or polar islands and usually occupy areas of less than 50,000 square kilometers. Unlike ice sheets, ice caps have a more localized impact, shaping the terrain directly beneath them, without affecting entire continents. Glaciers, meanwhile, are the most variable in size, ranging from small alpine glaciers to large valley glaciers. They often originate from ice caps or ice sheets and flow slowly downslope through valleys or across uneven terrain. Their motion is driven by gravity, enabling them to carve valleys, fjords, and other landforms over time. Because glaciers are more mobile and confined to specific regions, their erosional and depositional effects directly sculpt the landscapes they traverse. Understanding these distinctions provides a foundation for examining how glaciers actively reshape the land. Their movement, governed by gravity and temperature changes, generates powerful erosive forces that cut into bedrock and transport debris. At the same time as glaciers melt, they deposit sediments and rework the terrain, forming features such as moraines and outwash plains. This continuous balance between erosion and deposition lies at the heart of the transformative influence glaciers have had throughout Earth's history. Glaciers are powerful agents of landscape change, their immense mass and steady motion carving the forms we see today. As they move across the land, glaciers function both as sculptors and as builders, reshaping terrain through the constant interaction of erosion and deposition. This dual role is essential to understanding their impact on Earth's surface. Glacial erosion mainly takes place through processes like plucking and abrasion. Plucking occurs when meltwater seeps into cracks in the bedrock beneath a glacier and refreezes, loosening and lifting blocks of rock away from the surface. This process leaves behind uneven, rugged ground and contributes to the creation of distinctive features such as roches moutonnées with smooth, rounded slopes on one side and steep, jagged faces on the other. Abrasion works alongside this process, as rocks and debris embedded in the ice grind against the bedrock, producing fine rock flour, the powdered material generated by the glacier's grinding action, forming smooth grooves and highly polished rock surfaces. These characteristics act as long-lasting records of glacier motion, revealing both the direction and the strength of ice flow in the past. Deposition, by contrast, takes place when glaciers lose momentum, allowing the material they carry to be laid down and built up. As glaciers move forward or pull back, they release a wide range of sediments from very fine silt to massive boulders. Moraines, which are accumulations of debris along the glacier's sides, known as lateral moraines at its endpoint, called terminal moraines, or within the ice itself, referred to as medial moraines, are striking features produced by this process. These deposits not only trace the former reach of glaciers, but also shape later landscape development, forming fertile soils and clear boundaries between landforms. The interaction between glacial erosion and deposition creates a wide variety of geomorphological features, including U-shaped valleys, fjords, and drumlins, each carrying clear evidence of glacial influence. Through repeated advances and retreats, glaciers gradually carve the land their erosive force, exposing bedrock, while their deposited sediments continue to define terrain long after the ice has disappeared. Understanding these processes helps explain how glaciers have persistently shaped Earth's surface, leaving behind landscapes rich in geological detail and historical depth. Building on this understanding of glacial influence, it becomes necessary to examine the processes that control how glaciers move and flow, making these powerful erosional and depositional actions possible. The movement and flow of glaciers arise from a complex combination of physical mechanisms that enable enormous bodies of ice to travel great distances over time. Central to this motion is plastic deformation, a process in which the internal structure of ice slowly changes shape under pressure as layers of accumulated snow compress the ice below. Under these conditions, the ice behaves in a semi-fluid manner, allowing it to gradually bend and flow. This effect is strongest in the deeper and warmer parts of a glacier, where temperature and pressure favor deformation. Surface melting also plays an important role in glacier behavior. Meltwater that forms on the surface can seep down through crevasses and moulins to the glacier's base, where it lubricates the contact between the ice and the underlying bedrock. This lubrication lowers friction, allowing the glacier to slide more easily across its base. Such basal sliding often accounts for sudden increases in glacier speed or surges, particularly in temperate glaciers where surface melting is more common. Alongside internal deformation and basal sliding, the glacier's overall shape and the terrain beneath it strongly influence flow patterns. Steeper slopes tend to speed up movement, while uneven bedrock can create zones where the ice is compressed or stretched. As glaciers move over obstacles or encounter changes in slope, they frequently form crevasses, which serve not only as surface features, but also as visible signs of stress within the ice. These structures illustrate how glaciers dynamically respond to both internal forces and external conditions. Glacier flow is also shaped by climate, which affects accumulation and ablation rates, and therefore controls the glacier's overall mass balance. Changes in temperature, snowfall, and meltwater production can modify both the speed and direction of glacier movement over time. The delicate balance between internal deformation, basal sliding, and external influences gives glaciers their constantly changing character. Vast natural systems shaped by both their physical properties and their environment. Building on this understanding of glacier dynamics, it becomes important to explore how scientists estimate and reconstruct the size and volume of ancient ice sheets, providing valuable insight into Earth's climatic history. Estimating the size and volume of ancient ice sheets relies on a combination of innovative measurement methods and advanced modeling techniques grounded in both direct observations and indirect geological evidence. Because direct measurements are impossible for prehistoric times, researchers use a range of approaches to recreate past ice sheet configurations with impressive accuracy. One key method involves studying landforms created by glacial activity, such as U-shaped valleys, fjords, and drumlins, which act as physical records of former ice coverage. These features help define the reach and boundaries of ice sheets during different periods. Sediment deposits offer further crucial information. For instance, glacial till, which consists of unsorted material laid down directly by ice marks areas once covered by glaciers, while layered sediments can reveal changes in ice extent through time. Isotopic analysis of marine and lake sediments adds another layer of detail, allowing scientists to refine their reconstructions of ancient ice sheets and the climates in which they formed. For example, measurements of oxygen isotope ratios preserved in deep-sea sediment cores act as indicators of global ice volume. During glacial phases, lighter oxygen isotopes become more common in ocean water because expanding ice sheets draw large amounts of water out of the seas. These isotopic patterns, when examined alongside evidence from ice-rafted debris, allow scientists to estimate how much ice was stored on land. Progress in geophysical methods, including seismic imaging and gravity-based measurements, makes it possible for researchers to infer the thickness and internal composition of surviving ice sheets and to reconstruct the former reach of much larger ice masses by extending these observations backward in time. Computer simulations then bring together these varied data sets, modeling how ice sheets grew and diminished by factoring in climate conditions, surface topography, and interactions with the underlying bedrock. When calibrated using geological evidence, these models help scientists produce detailed reconstructions of ice sheet development, offering estimates of their total volume and their effects on global sea levels. Through this broad, multidisciplinary strategy, which blends landform studies, sediment analysis, isotope research, and numerical modeling, scientists gradually assemble the complex history of Earth's ice sheets. This continuing synthesis enriches our understanding of how these vast bodies of ice expanded and retreated across immense spans of time, shaping climate patterns and landscapes long before written records existed. The traces of ancient glaciers and ice sheets remain etched into Earth's geological archive, providing essential clues about their past size and behavior. One of the most striking forms of evidence is the presence of striations, long and linear grooves carved directly into bedrock by the persistent movement of glacial ice. These deep scratches not only reveal the direction in which ice once flowed, but also testify to the tremendous pressure exerted over thousands of years. Frequently, such striations appear alongside smooth, polished rock surfaces, created by the grinding action of debris frozen into the base of the ice. Beyond these surface features, scientists also identify a range of distinctive landforms produced by glacial processes. Moraines, which are ridges made of unsorted material known as till, and deposited along glacier edges, mark former ice limits. Terminal moraines, for example, indicate the furthest point a glacier reached during its maximum advance. Lateral moraines, by contrast, develop along the sides of glaciers, tracing their earlier boundaries. Some of these features extend for hundreds of kilometers, offering a clear and physical record of fluctuations in ice sheet extent. Subglacial lakes and sediment layers add further important evidence. As glaciers melt or withdraw, they often leave behind finely layered sediments called varves, annual deposits of silt and clay that capture seasonal changes. By counting these varves, scientists can reconstruct variations in ice sheet size across thousands of years. In addition, the presence of dropstones, Large rocks carried by ice and released into much finer sediments signals the movement of icebergs, carved from ice sheets into surrounding waters. Ice-rafted debris preserved in marine sediments strengthens this picture of glacial reach. When ice sheets produce icebergs, they transport rocky material that is eventually released as the ice melts and sinks, leaving a scattered trail of debris across the ocean floor. Studying these deposits allows researchers to map the timing of glacial advances and retreats. When all these strands of evidence are brought together, including bedrock markings, landforms, sediments, and transported debris, they form a detailed account of how glaciers and ice sheets expanded and contracted throughout Earth's climatic past, highlighting the dynamic nature of ice during the ice ages. Ice sheets, enormous bodies of glacial ice that once covered vast areas of continents, play a major role in controlling global sea levels during ice age intervals. As these immense ice masses build up, they trap huge quantities of fresh water, reducing the volume of water held in the oceans. This storage leads to a significant fall in sea level, often by as much as 120 meters, compared with present-day levels during periods of maximum glaciation. Such substantial drops expose continental shelves and create land bridges, dramatically reshaping coastlines and opening migration routes for both humans and animals. When the climate warms and an ice age gradually recedes, glaciers and ice sheets melt, releasing their stored water back into the oceans. Sea levels then rise, sometimes very quickly, inundating low-lying coastal areas and transforming the planet's geography once again. The rise and fall of these ice masses are controlled by intricate interactions among atmospheric temperatures, ocean circulation, and variations in Earth's orbit, producing a repeating cycle of glaciation and deglaciation that has marked Earth's history time and again. The magnitude of these transformations highlights the powerful role ice sheets play within global climate systems. As they spread, they cool the Earth further by bouncing sunlight back into space through their highly reflective surfaces, while their withdrawal hastens warming by permitting greater amounts of solar energy to be absorbed by oceans and land. These feedback processes illustrate the fine balance that exists within Earth's climate and draw attention to how sensitive sea levels are to the expansion or melting of ice sheets. Exploring the connection between ice sheets and sea levels helps reveal the wider narrative of Earth's climate changes. It shows how natural forces have repeatedly reshaped the planet's geography, influencing sea passages, ecosystems, and human societies alike. By examining past glacial cycles, scientists gain important clues about possible future changes driven by ongoing climate shifts. This understanding not only enriches our appreciation of Earth's ever-changing past, but also stresses the importance of closely observing present-day ice sheet behavior, given its direct influence on sea level stability and overall global climate health. From these insights, it is natural to begin wondering which kinds of plants were able to survive and even flourish under the harsh and unforgiving conditions of the Ice Age. How did they manage to adapt to such extreme environments? During the frozen chapters of the Ice Age, plant life faced severe challenges that required extraordinary adaptations to endure. While attention often focuses on the large animals that moved across these icy landscapes, Resilient plant communities were essential in supporting entire ecosystems. Cold regions were dominated by tundra and steppe vegetation, made up of tough, low-growing plants that reduced exposure to fierce winds and bitter temperatures. These included mosses, lichens, dwarf shrubs, and grasses, each displaying distinctive strategies that allowed them to persist in such demanding settings. Lichens, a symbiotic union of fungi and algae, stand out for their exceptional toughness. They can withstand long periods without moisture and intense cold, often surviving on bare rock where other plants cannot take hold. Their capacity to carry out photosynthesis at low temperatures enabled them to act as crucial early settlers in desolate landscapes. Dwarf shrubs such as Arctic willow and crowberry evolved compact ground-hugging shapes that limited wind exposure and helped retain warmth. These plants typically developed small, thick leaves with waxy surfaces that reduced water loss, an essential adaptation in environments where liquid water was scarce beneath vast ice sheets. Grasses and sedges, supported by widespread root systems, were able to sprout rapidly whenever conditions briefly improved, taking advantage of short warmer intervals within glacial cycles. Their growth patterns and reproductive methods, including the production of seeds capable of traveling long distances, allowed them to colonize new regions efficiently. Many of these plants also entered dormant states during the coldest phases, restarting growth as temperatures increased. This physiological flexibility was key for surviving the extreme seasonal swings typical of Ice Age climates. Such adaptations not only allowed these plants to endure, but also prepared the foundation for later ecological succession. Their continued presence created small habitats that supported insects, small mammals, and eventually larger animals. In this frozen world, life persisted through resilience and ingenuity, adapting to one of the most challenging climates Earth has ever known. Continuing this story of endurance, it is natural to ask which animal species were able to survive these icy conditions and how they coped with relentless cold. During the Ice Age, certain animals came to prominence by developing remarkable traits that enabled them to withstand extreme temperatures, limited food supplies, and shifting landscapes. These megafauna not only influenced their environments but also demonstrated resilience through specialized physical features and behaviors suited to life in frozen worlds. Mammoths, among the most recognizable Ice Age creatures, were covered in dense, layered fur that insulated them from severe cold. Their long, curved tusks served several purposes, including clearing snow to reach food and defending against threats. Their massive bodies followed Rutherford Bergman's rule, helping them retain heat by minimizing surface area relative to volume. Mammoths were also skilled at digging through snow and ice to reach grasses, shrubs, and other plants hidden below the frozen ground, showing their ability to cope with seasonal shortages. In a similar way, saber-toothed cats, armed with their strikingly long canine teeth, were apex predators finely adapted for bringing down large herbivores. Their strong physiques and compact, powerful limbs enabled sudden bursts of speed, an ability essential for surprising prey across open tundra environments. Heavy jaws paired with broad skulls supported formidable biting force, while razor-sharp teeth were adapted for cutting through flesh, allowing them to remain efficient hunters, even under harsh conditions. Some findings indicate they may have possessed thick fur or other insulating traits, improving their chances of survival in colder habitats. Giant ground sloths, including species such as Megatherium, were adapted to a lifestyle defined by slow, deliberate movement across open plains and wooded areas. Their enormous bodies were cloaked in coarse fur, and their long, curved claws allowed them to pull down branches and reach leaves from tall trees and shrubs. A low metabolic rate, combined with their great body mass, helped retain heat, enabling them to withstand colder climates. As herbivores, they depended on browsing whatever vegetation was available, even during severe winters, with their sheer size providing an advantage in conserving warmth. Together, these animals demonstrate the remarkable adaptations that allowed Ice Age megafauna to thrive despite environmental pressures. Their physical forms and behaviors reveal a careful balance between specialization and toughness, supporting survival during a time marked by persistent cold and ecological disruption. This endurance invites an intriguing question. How did other megafauna, such as mammoths, saber-toothed cats, and giant sloths, succeed in surviving the extreme conditions of the Ice Age? The survival methods of Ice Age megafauna, including mammoths, saber-toothed cats, and giant sloths, display extraordinary adjustments to the frozen environments they occupied. These animals developed traits that allowed them to cope with severe cold and limited resources conditions, typical of glacial periods. Thick layers of insulating fat and dense coats of fur provided critical warmth, forming protection against freezing winds and low temperatures. Mammoths, for example, were equipped with a heavy woolly covering and a substantial fat layer that functioned both as insulation and as stored energy during long, unforgiving winters. In addition to physical traits, behavioral adaptations were equally important. Many species undertook seasonal migrations, moving in response to food availability and avoiding the most extreme conditions. Their social organization further enhanced survival, as living in groups offered defense against predators and enabled cooperative care for young and injured members. Saber-toothed cats, though formidable predators, likely depended on ambush strategies and natural cover to hunt successfully, while giant sloths used their immense strength to feed on tough, browse-rich plants that remained accessible even beneath snow. Flexibility in diet was another key factor in their resilience. Numerous megafauna species were capable of consuming a broad range of plant materials, including twigs, shrubs, and roots, which could still be found during winter when grasses were scarce. Their digestive systems evolved to extract maximum nutrition from these lower-quality food sources, helping them endure the most difficult periods. Some species also possessed specialized physical features that directly addressed environmental challenges. Mammoths, for instance, had long curved tusks used to clear snow and ice to uncover buried plants. Their thick limb bones and wide feet reduced the risk of sinking into snow, allowing easier movement across frozen ground. The impressive adaptations seen in these megafauna illustrate a complex interaction of anatomy, behavior, and ecological strategy that supported life in some of the coldest regions on Earth during the Ice Age. Their capacity to persist highlights the remarkable adaptability of life when confronted with extreme climatic stress, paving the way for understanding how evidence of these ancient ecosystems is revealed today. Fossilized bones, preserved remains, and many other geological indicators form the foundation of our knowledge of Ice Age ecosystems. These traces open a window onto a long-lost world, showing the variety of species that once occupied vast frozen landscapes. Large megafauna, such as mammoths, mastodons, and giant sloths, have left behind extensive skeletal remains, frequently discovered in permafrost or embedded within layers of sediment. Such fossils not only verify that these animals existed, but also offer information about their size, diet, and aspects of their behavior. In rare cases, preserved soft tissues, including hair, skin, and even stomach contents, have been recovered from exceptionally well-preserved specimens. These extraordinary discoveries allow scientists to examine ancient DNA, reconstruct evolutionary lineages, and investigate relationships between extinct animals and those alive today. DNA obtained from mammoth remains, for example, has provided valuable insight into their migration routes and the ways they adapted to shifting climates. In a similar way, pollen grains and preserved plant remains trapped within ice cores, and layers of sediment reveal which kinds of vegetation sustain these ecosystems, showing how plant communities changed as glaciers advanced and withdrew. The examination of cave paintings and carved figures also deepens our understanding, providing visual records of the animals that lived during the Ice Age. When these artistic portrayals are considered alongside physical remains, they allow researchers to reconstruct the intricate network of predator-prey interactions and habitat preferences. Isotope analysis of fossilized bones adds yet another layer of insight, shedding light on the diets of extinct animals and their patterns of movement, and revealing how they reacted to shifts in their environment. Together, these varied forms of evidence rebuild a picture of dynamic ecosystems defined by a rich interaction between animals, plants, and climate. They reveal not only the diversity of Ice Age worlds, but also the powerful influence that climatic changes had on these ancient communities. As we look further into this frozen past, the accumulating evidence continues to show just how complex and resilient these ecosystems once were, laying the groundwork for understanding the dramatic transformations that ultimately led to their disappearance. This progression naturally encourages us to examine how and why so many of these extraordinary species vanished, and to consider the main hypotheses proposed to explain such a profound loss. The extinction of many Ice Age species remains an area of intense scientific investigation, with several theories offered to account for these events. As glaciers repeatedly advanced and retreated across immense regions, environmental conditions shifted sharply, disrupting the fragile balance of ecosystems. Many species once well adapted to icy tundra or broad steppe landscapes encountered sudden habitat loss, leaving them with the stark choice of rapid adaptation or extinction. The most widely supported explanations for these disappearances often point to a combination of climate change and human influence. Climatic transitions toward the end of the Ice Age slowly converted frozen environments into more temperate ones. For cold-adapted megafauna, such as mammoths, mastodons, and giant ground sloths, this meant reduced living space and diminishing food supplies. As temperatures increased, the grasslands and steppe habitats, they relied upon shrank, forcing populations into smaller refuges or isolated areas. Without the ability to adapt quickly or migrate effectively, many groups declined and ultimately died out. Evidence indicates that the speed of climatic change exceeded their capacity to evolve or relocate, resulting in widespread extinctions. The arrival of humans introduced an additional challenge. Early human populations, equipped with increasingly advanced tools, moved into and made use of new regions. Overhunting likely played a role in the decline of certain species, particularly those already weakened by environmental change. The expansion of human presence into Ice Age ecosystems aligns closely with the timing of many extinctions, fueling ongoing debate over the relative impact of human activity compared to climatic forces. Some researchers also point to disease and ecological competition, suggesting that new predators or competitors, brought by migrating humans or other species, further destabilized already vulnerable populations. Moreover, genetic evidence suggests that small isolated groups suffered from inbreeding depression, which reduced their ability to cope with environmental stress. Taken together, the extinction of Ice Age species appears to have arisen from a complex interaction of changing climates, human pressures, and ecological processes. This tangled combination of factors highlights how vulnerable species can be when faced with rapid environmental change, a lesson that echoes strongly in discussions of both ancient and modern biodiversity crises. Exploring this theme further naturally leads to questions about how plants and animals attempted to cope with these challenges through movement and evolutionary change. As the Ice Age waxed and waned, shifting climatic conditions placed constant pressure on both plant and animal populations, pushing them to develop new strategies for survival. Migration emerged as one of the most important responses. Species relocated in search of more favorable conditions, often traveling enormous distances across ice-covered regions, open tundra and wooded pathways. Large herbivores, such as mammoths and reindeer, for example, followed the changing margins of ice sheets, tracking areas where vegetation persisted within refugia, small zones where conditions remained comparatively stable. These refugia served as vital havens, enabling species to endure periods of severe cold and widespread habitat loss. Alongside migration, many organisms developed extraordinary adaptations that allowed them to survive the harsh demands of a frozen world. Plants, for instance, evolved anti-freeze proteins that stopped ice crystals from forming inside their tissues, allowing them to withstand sub-zero temperatures. Some species adopted distinctive growth forms, including low-growing shrubs and mosses, which reduced their exposure to fierce winds and intense cold. Many perennial plants entered periods of dormancy during the coldest months, preserving energy until environmental conditions became more favorable. Among animals, adaptations such as thicker fur, greater fat reserves, and behaviors like burrowing or hibernation became common in mammals. The woolly mammoth, with its heavy coat and large, fatty hump, became a clear symbol of these evolutionary solutions, focused on insulation and energy storage. In addition, certain species adjusted their reproductive cycles to align with more favorable seasons, increasing the likelihood that their offspring would survive. Some animals developed seasonal migration routes that matched changes in food availability, effectively following shifting ecosystems across the landscape. This constant interaction between migration and adaptation not only supported individual survival, but also shaped entire communities, influencing predator-prey relationships and determining how species were distributed across continents. These survival strategies reveal the extraordinary resilience of life in the face of ongoing environmental change. As climates continued to fluctuate, both plants and animals refined their responses, laying the groundwork for increasingly complex ecological relationships. Exploring how these organisms endured the extreme conditions of the Ice Age encourages deeper reflection on how predator-prey dynamics evolved during such sweeping transformation. During the Ice Age, relationships between predators and prey changed dramatically under the pressure of a shifting environment and the constant challenge of survival. As glaciers spread and climates became more severe, species distributions and population sizes shifted rapidly, forcing both hunters and hunted to adapt quickly. Large herbivores moved across vast frozen plains, developing new ways to avoid predators that were becoming ever more specialized. At the same time, predators such as saber-toothed cats and giant wolves evolved powerful traits including elongated canines, strong limbs, and sharp senses, enabling them to exploit plentiful prey with greater efficiency. Scarce resources in icy landscapes raised the stakes of these encounters. Predators often depended on endurance hunting tracking prey across wide territories, while prey species developed heightened awareness, stronger herd behavior, and faster escape responses. The evolution of these interactions became a continuous arms race. Prey grew quicker, more vigilant, and more social, while predators refined their hunting strategies and physical adaptations. For instance, some predators specialized in ambush tactics, while others evolved for long-distance pursuit, adjusting their bodies to cope with cold, open environments. The predator-prey dynamic also shaped broader evolutionary trends. In certain cases, intense selective pressures produced highly specialized species, each finely adapted to survive in the frozen wilderness. The need for effective hunting drove predators toward innovations such as enhanced sensory organs or stronger bite forces, while prey diversified into multiple forms to occupy different ecological niches or avoid predation altogether. This ongoing evolutionary interplay contributed to the striking biodiversity seen during the Ice Age. The adaptations forged through these predator-prey relationships not only determined how individual species survived, but also influenced community structures and ecological balance, highlighting how life continued to persist and even flourish under icy extremes. It becomes evident that these interactions were powerful engines of evolutionary change, shaping the complex web of life that emerged after the ice retreated. Their influence extends far beyond the Ice Age, forming the foundation for the intricate evolutionary pathways observed in modern ecosystems. This shared history shows that survival in a frozen world required constant negotiation, balancing the predator's relentless pursuit with the prey's clever strategies, ultimately driving the unstoppable process of evolution. The plants and animals of the Ice Age deeply shaped the course of Earth's evolutionary history, acting as both designers and catalysts for change across countless species. As glaciers advanced and withdrew in repeating cycles, ecosystems were reshaped again and again, encouraging adaptations that defined how many organisms would survive. Cold-tolerant plants such as mosses, lichens, and hardy grasses flourished across tundra environments, creating resilient habitats that sustained a wide range of herbivores. These plants did far more than simply support vast megafauna, such as mammoths, mastodons, and giant deer. They also formed intricate food networks that tightly linked the destinies of predators and their prey. Large grazing animals, in turn, had a powerful influence on the landscapes they inhabited. Through their feeding habits, they shaped the distribution of vegetation, helping to preserve open terrains that favored certain plant communities rather than dense forests. Because of their great size and ability to move across long distances, these animals could roam enormous frozen regions, often functioning as keystone species that determined the overall structure of their ecosystems. Their existence and later their disappearance as a result of climatic changes and human influence triggered major ecological shifts, revealing just how fragile and finely balanced Ice Age environments truly were. The relationship between plants and animals during this era also drove significant evolutionary developments. Many mammals, for instance, evolved thick fur coats and substantial fat layers as direct adaptations to extreme cold, while some plant species developed strategies that allowed them to endure freezing temperatures and reduced sunlight. These traits not only made survival possible during repeated glacial cycles, but also set the stage for future evolutionary directions. As the Ice Age continued, changing climates and mounting environmental pressures encouraged species to diversify and migrate. The evolving landscape created pathways and obstacles alike, shaping patterns of speciation and extinction. These constantly shifting interactions between climate plants and animals ultimately crafted the rich biological mosaic we see today, emphasizing their essential role in Earth's evolutionary story. Recognizing this deeply connected history invites a fuller understanding of how life on our planet continuously adjusts and transforms in response to planetary rhythms. The frozen environments of the Ice Age did more than mold the physical surface of the world. They profoundly influenced the path of human evolution and movement. As glaciers advanced and withdrew in steady cycles, early humans were forced to respond quickly to ever-changing conditions. These climatic shifts produced a mosaic of livable regions, often separated by immense ice sheets and tundra, encouraging both the diversification of human groups and their migration across vast distances. Life in cold regions demanded creative survival solutions. Early humans crafted new tools designed for hunting large Ice Age animals such as mammoths and reindeer species well adapted to frozen climates. The challenge of securing limited resources pushed technological progress forward, including the development of specialized weapons and protective clothing made from animal hides. Such innovations not only improved survival, but also supported the emergence of complex social structures and cultural traditions. Patterns of migration during the Ice Age were closely tied to changes in climate. When ice sheets expanded, human populations withdrew into refugia regions with milder conditions, including southern Europe, the Middle East, and parts of Asia. During warmer intervals, these groups spread outward again, sometimes traversing land bridges like Beringia, exposed by lowered sea levels. These movements enabled Homo sapiens and other hominin species to disperse widely across continents, promoting genetic mixing and the exchange of ideas and culture. Harsh climates also applied strong evolutionary pressure, favoring physical traits suited to cold conditions. In northern populations, for example, increased body fat and broader limbs became more common adaptations that improved heat retention. Over many thousands of years, such traits became deeply embedded, showing how climate influenced not only where humans traveled, but also how their bodies evolved. Ultimately, the ever-changing climate of the Ice Age acted both as an obstacle and a driving force for human progress. It compelled our ancestors to innovate, adapt, and migrate in ways that laid the foundation for the diversity and resilience seen in modern humans. As we examine traces of early settlements and human activity from this frozen era, we uncover a powerful story of endurance and creativity woven into our origins. Archaeological evidence of Ice Age habitation offers a clear picture of how early humans managed life in landscapes reshaped by persistent cold and shifting terrain. Excavations show that human groups established semi-permanent camps in carefully chosen locations, often close to vital resources such as rivers, lakes, or animal migration paths. Remains, including stone tools, fire hearths, and animal bones, provide concrete proof of human life thriving amid the harsh, icy surroundings. One of the most persuasive lines of evidence comes from the identification of shelter remains buried beneath layers of ice and sediment in places such as the Paleolithic cave systems of Europe. In locations across France and Spain, cave paintings portray scenes of hunting and everyday activities, pointing not only to sustained human presence, but also to symbolic thinking and strong social connections. These artistic works, some created tens of thousands of years ago, reveal that early humans practiced sophisticated cultural behaviors even while living in extremely demanding environments. Additional insights arise from the diversity and refinement of tools uncovered at these sites. Scrapers' blades and projectile points made from stone bone and ivory show carefully developed techniques suited to hunting large Ice Age animals such as mammoths, reindeer, and bison. The existence of tools designed for particular purposes reflects a detailed understanding of local conditions and thoughtful use of available resources. Moreover, the finding of animal bones marked by cuts offers clear proof of butchering activities, shedding light on subsistence methods. In several areas, traces of clothing and shelter construction further illustrate adaptive creativity. For instance, preserved animal skins and bone frameworks indicate that early humans fashioned insulating clothing and movable shelters to cope with the cold. These advances not only supported survival, but also strengthened social ties and allowed skills to be passed from one generation to the next. Taken together, these archaeological signs, settlement evidence, artwork tools, and remains create a portrait of resilient groups actively shaping their surroundings despite the hardships of the Ice Age. They highlight an impressive ability to adapt, establishing the basis for later stages of human evolution through physical and cultural strategies that made life possible in such severe conditions. As we examine these responses more closely, the narrative of human resilience grows even more striking, revealing an ongoing interaction between environment and innovation. Confronted with the persistent cold of the Ice Age, humans displayed exceptional creativity in both bodily adaptations and cultural developments. On a physical level, our ancestors evolved characteristics that improved their chances of surviving in cold climates. For example, wider bodies and shorter limbs. Traits described by Bergmann's and Allen's rules helped retain heat by lowering surface area relative to body volume. A more compact physique reduced heat loss, while increased layers of subcutaneous fat offered essential insulation, creating a natural barrier beneath the skin. In addition, some populations developed larger nasal cavities, which may have warmed cold air before it entered the lungs, further supporting temperature regulation. Alongside these anatomical changes, humans adapted culturally, adopting behaviors that worked in harmony with their biology. Clothing became vital, with early communities producing garments from animal hides and furs. These materials provided insulation, preserving body heat and protecting against freezing winds. The significance of clothing was so great that it likely shaped social organization, encouraging cooperation in hunting and in preparing animal skins for warmth. Shelter building also advanced as people constructed semi-permanent homes from bones, hides, and earth designed to conserve heat and endure severe weather. Fire emerged as a central element of survival, as well supplying warmth and enabling cooking, which released nutrients from food and made meals easier to digest. Social collaboration was equally important. Sharing food, working together in hunts, and maintaining communal fires all increased survival prospects for individuals and groups living in cold regions. These cultural practices also supported the transfer of survival knowledge across generations, building shared resilience against unyielding cold. Together, these adaptations, biological features, clothing, shelters, fire use, and social cooperation formed a unified strategy for survival. They demonstrate a complex relationship between biology and culture, showing how humans not only survived but flourished under the Ice Age's frozen conditions. As we reflect on these approaches, it becomes evident that our ancestors' creativity reached far beyond basic survival, helping to shape enduring patterns of human resilience that still influence us today. This gradual development naturally leads us to consider the particular tools and technologies that further strengthen their ability to endure such extreme cold. Ice Age humans showed outstanding inventiveness in creating tools and technologies specifically suited to life in a harsh, icy world. Confronted with constant cold, they produced specialized equipment not only for hunting and gathering, but also for maintaining warmth and protection in an environment where survival depended on careful adaptation. One of their most important breakthroughs was the development of clothing made from animal hides and fur, which offered vital protection against the cold. To prepare these materials properly, they created sharp stone blades and scrapers, turning raw skins into usable garments. Over many generations, these tools gradually improved with sharper, more precise edges suited for cutting and sewing, enabling humans to produce layered clothing that reduced heat loss more effectively. Advances in shelter construction were also driven by harsh climatic conditions. Early humans built temporary shelters using animal bones, wood, and hides. Designed specifically to retain warmth, these structures reflected a growing ability to use natural materials to create insulated hearths and fire pits, which functioned both as sources of heat and as focal points for social interaction. Fire itself became an essential technology, not only providing warmth, but also allowing food to be cooked, improving nutrition and energy intake, which was especially important in a resource-scarce environment. The development of reliable fire-making methods, such as striking flint to create sparks, represented a major technological achievement. Beyond clothing and fire, Ice Age humans also produced composite tools that combined stone with bone or antler. These tools, made from multiple materials, improved efficiency in hunting and processing animals, a necessity when resources were limited. For instance, spear throwers, or atlatls, increased both the distance and power of projectiles, allowing hunters to take down large prey from safer positions. The capacity to create durable multifunctional tools shows a clear understanding of material properties and a flexible problem-solving mindset that was crucial for survival in a cold and unpredictable climate. Taken together, these technological developments demonstrate a remarkable ability to adapt to the environmental pressures of the Ice Age. They reveal not only skill in working with raw materials, but also a growing awareness of how to shape the surrounding environment to meet basic needs. As tools and techniques became more refined, humans established the foundations for increasingly complex behaviors and social cooperation, paving the way for later evolutionary and cultural change. These achievements illustrate the resilience and creativity that defined human life during one of the most challenging climatic periods in Earth's history. During the Ice Age, hunting and gathering practices became steadily more advanced as people responded to difficult conditions and changing resource availability. Early humans were forced to adjust their strategies constantly, developing a detailed understanding of landscapes and animal behavior. At first, small groups depended on simple persistence, hunting pursuing animals over long distances until they were exhausted, a method well suited to open, cold environments inhabited by large prey. With growing experience, humans improved their techniques using coordinated ambushes and specially crafted tools such as spears and atlatls to increase hunting success. These innovations made it possible to hunt large animals like mammoths, bison, and reindeer more efficiently, providing essential food as well as materials for shelters and clothing. Gathering practices also became more sophisticated over time. Early humans learned to take advantage of seasonal plant resources, following the cycles of fruits, nuts, and tubers across different landscapes. They developed an understanding of microclimates and ecological zones, allowing them to move deliberately to maximize resource collection during times of scarcity. This seasonal movement demanded adaptable social organization and effective communication, encouraging cooperation within groups. The creation of tools for processing plant foods, including scrapers and grinding stones, further improved their ability to extract nutrition from available vegetation. As reliance on a wider range of resources increased, humans also developed storage methods such as drying and fermenting food, extending the usefulness of gathered supplies through long, harsh winters. These adaptive approaches not only supported survival, but also strengthened social bonds and facilitated the sharing of knowledge, both of which were crucial in the development of early human cultures. The need to exploit many different resources also encouraged further technological innovation, including the production of more specialized tools for specific tasks. Hunting and gathering systems during the Ice Age became increasingly intricate as humans navigated an unpredictable world. The constant pressure to survive in frozen conditions stimulated innovations that laid the foundation for more advanced behaviors. As these survival strategies continued to evolve, they influenced the emergence of symbolic and artistic expression, pointing to a deeper cognitive relationship with the environment. This gradual shift toward symbolic behavior suggests a strong connection between environmental challenges and the growth of human culture. The harsh and striking landscapes of the Ice Age formed a distinctive backdrop that deeply shaped the rise of early art and symbolic behavior within human groups. As glaciers carved and reshaped the land, people responded not only by developing ways to survive, but also by expressing how they related to the world around them. Cave paintings, engravings, and items of personal decoration represent some of the earliest signs of symbolic thinking, revealing an ability for abstract expression that went beyond immediate practical concerns. The enclosed and at times naturally lit interiors of caves became places of refuge for creative activity. Within these shadowed spaces, early humans painted figures of animals such as bison horses and reindeer using natural pigments made from ochre and charcoal. These images likely carried symbolic or ritual meaning, possibly connected to hunting practices or spiritual beliefs meant to influence success in the hunt or to honor the animals portrayed. The repeated focus on animal imagery across wide regions points to shared cultural values and an emerging sense of collective identity, grounded in the surrounding environment. Beyond cave art, personal ornaments such as shell beads and animal teeth demonstrate an awareness of symbolism and social meaning. These objects may have represented social connections, individual identity, or involvement in communal rituals. In a severe climate where durable materials were rare, the items that could be preserved may have taken on heightened importance, transforming simple objects into potent symbols. Symbolic behavior also appeared in practices involving the body and ritual actions. Evidence of deliberate burials accompanied by grave goods suggests beliefs surrounding death and an understanding of existence beyond the physical body. This spiritual dimension, expressed through symbolic acts, highlights how early humans used art not just as a form of communication, but as a way to interpret and engage with their environment and their own place within it. These behaviors imply that the Ice Age environment did more than influence survival strategies. It nurtured a mental landscape in which symbols, stories, and spiritual concepts became central to human life. As people faced an unpredictable climate, creative expression offered a means to interpret events, exert influence, and discover meaning within a world in constant flux. The shifting climate of the Ice Age had a profound impact on human population dynamics, serving both as an obstacle and a driver for migration, adaptation, and survival. Changes in temperature and environmental conditions led to fluctuations in the availability of resources, forcing early humans to respond with exceptional resilience and creativity. During colder intervals, expanding ice sheets and falling temperatures reduced habitable areas, compressing populations into refugia regions where conditions remained manageable. These refugia often became centers of population concentration, promoting genetic exchange and encouraging cultural innovations essential for surviving harsher environments. In contrast, warmer interglacial periods opened access to new lands, allowing humans to move into areas that had previously been uninhabitable. As ice retreated, newly exposed landscapes offered fresh food sources, including migrating animals and a wider variety of plant life. These warmer phases supported population growth and movement, spreading human groups across Eurasia and beyond. Yet such expansions were rarely stable. Rapid climatic changes could result in sudden habitat loss, forcing populations to withdraw or adapt quickly. This recurring pattern of contraction and expansion produced a highly dynamic demographic landscape marked by periodic population bottlenecks and bursts of growth that shaped genetic diversity and evolutionary pathways. Climatic variability also influenced technological progress and social structures. When resources were scarce, groups developed new tools for hunting and gathering, while environmental pressures encouraged more complex social organization focused on cooperation and shared survival. Evidence indicates that during colder phases, humans created more advanced clothing shelters and hunting methods to endure extreme conditions. These adaptations not only supported immediate survival, but also formed the foundation for cultural and technological developments passed down through generations. Examining how climatic shifts affected human population patterns during the Ice Age reveals the depth of human adaptability and resilience. It emphasizes the crucial role of environmental forces in shaping our evolutionary past and provides insight into how our ancestors navigated a challenging and ever-changing world. As we explore these processes more closely, it becomes evident that climate was far more than a passive setting. It was a powerful force shaping the course of human evolution, a realization that naturally highlights the role of archaeological discoveries in revealing this intricate past. The unearthing of Cro-Magnon and Neanderthal remains has significantly transformed our understanding of how humans adapted and survived during the Ice Age. These ancient skeletal remains act as direct connections to our evolutionary history, providing essential clues about how early humans coped with a world defined by extreme cold, shifting environments and limited resources. Neanderthal skeletons, for example, display clear physical traits suited to severe climates, including strong compact bodies, stocky proportions, and enlarged nasal passages that likely helped warm frigid air before it entered the lungs. Such characteristics demonstrate how human biology adjusted to the demands of glacial conditions. Cro-Magnon remains representing early Homo sapiens point to a major evolutionary step toward advanced tool-making, cultural creativity, and complex social structures. Their well-preserved fossils reveal signs of sophisticated behavior ranging from the production of detailed tools and personal ornaments to participation in symbolic rituals. These developments not only increased their chances of surviving the challenges of the Ice Age, but also signaled the beginning of cultural evolution that would eventually give rise to modern humans. Placing Neanderthal and Cro-Magnon remains side by side reveals a narrative of both competition and interaction, suggesting a dynamic relationship with lasting consequences for human genetic history. These findings extend well beyond the study of bones alone. They offer a vivid portrait of human resilience and inventiveness in an unforgiving climate. Archaeological evidence found alongside these remains, including Hearth's cave art and tools, further clarifies how early humans used their surroundings, hunted large animals, and formed social connections essential for surviving the cold. This evidence highlights the importance of adaptability not only in biological terms, but also in cultural practices during an era of constant environmental change. Studying these ancient remains places the broader story of human evolution within the context of the Ice Age. It reinforces the idea that our ancestors were not helpless in the face of nature, but active participants shaping their own futures. As we look more deeply into how early humans managed to survive and flourish in such a frozen world, it becomes clear that their history is closely linked to Earth's dramatic climatic shifts. This understanding provides a foundation for examining how glaciers and ice sheets physically altered the planet's surface, reshaping landscapes and influencing the direction of human history. As vast sheets of ice advanced and withdrew across the land, their tremendous power reshaped Earth's surface in ways that remain visible today. Glaciers and ice sheets, functioning like slow-moving geological artists, cut through solid bedrock, transforming valleys and plains with steady, relentless force. Their motion, driven by gravity, caused immense masses of ice to spread outward from thick accumulations in polar regions and high-altitude areas. This gradual but persistent movement applied enormous pressure to the ground below, triggering a variety of erosional and depositional processes that permanently altered the landscape. One of the main ways glaciers modified the land was through erosion. As they moved forward, glaciers scraped and ground the surface beneath them, using trapped debris and ice crystals like natural abrasives. This action widened and deepened existing valleys, changing narrow V-shaped river valleys into wide U-shaped channels. The sheer weight and motion of the ice also stripped away soil and loose rock, revealing bedrock and producing rugged, dramatic terrain. Alongside erosion, glaciers also deposited huge amounts of material known as glacial till as they melted. These deposits built up in different forms, creating features such as moraines, ridges of unsorted debris that mark the furthest reach of advancing ice. When glaciers retreated, they often left landscapes scattered with lakes and wetlands, formed as meltwater collected in depressions carved by ice or trapped behind terminal moraines. The immense scale of glacial activity also produced distinctive landforms that record the presence of ancient ice sheets. Structures such as drumlins, elongated hills shaped by flowing ice, and eskers, long winding ridges created by sediment carried within subglacial meltwater channels, stand as quiet evidence of these powerful processes. These landforms not only reveal the movements of ice in the distant past, but continue to shape the geography and ecosystems of the regions where they exist today. Through these ongoing processes, glaciers and vast ice sheets have permanently transformed Earth's surface, leaving behind landscapes of striking scale and intricate detail that reflect a long history of persistent icy change. Glacial activity has carved some of the planet's most dramatic and easily recognized landforms, preserving features that clearly document the movement and influence of ice through time. Among the most notable of these are U-shaped valleys and fjords, distinctive imprints of glacial erosion that each reveal different aspects of the power and progression of moving ice. U-shaped valleys, often called glacial troughs, develop as advancing glaciers relentlessly erode pre-existing river valleys. Unlike river-cut valleys, which are typically V-shaped due to flowing water, glaciers grind out broad, deep channels with steep, sometimes nearly vertical walls. As ice moves forward, it widens and deepens the original V-shaped valley through mechanisms such as plucking and abrasion. The outcome is a wide valley with a flat floor and a pronounced U-shaped profile, frequently accompanied by hanging valleys, where smaller tributary glaciers once merged with the main ice flow. These features stand as lasting proof of extensive glacial erosion, demonstrating the enormous mass and slow, powerful movement of ice over thousands of years. Fjords, by contrast, represent a specialized form of U-shaped valley that has been submerged by rising sea levels. They are commonly found in places where glaciers once carved deep, steep-sided valleys, below present-day sea level, including regions like Norway, New Zealand, and parts of Canada. When glaciers retreat and seawater fills these carved depressions, fjords emerge as long, narrow inlets bordered by towering cliffs. Their creation depends on intense glacial erosion, followed by sea level rise that inundates the valleys. Fjords are often noted for their great depth and striking scenery, making them some of the most iconic examples of glacially shaped coastlines. Together, U-shaped valleys and fjords illustrate the immense forces active during the Ice Age. Their existence reflects not only the erosive strength of glaciers, but also the dynamic relationships between ice land and sea. These landforms are far more than scenic features. They are essential records that help reveal the extent, movement, and retreat of glaciers throughout Earth's history. As we look further into this story, it becomes important to examine how smaller glacial features such as moraines, drumlins, and eskers continue to shed light on the legacy of ancient ice sheets and their profound influence on the landscape. As glaciers advanced and withdrew across the terrain, they created a wide range of distinctive landforms that remain as quiet testimony to their ancient paths. Among these moraines, drumlins and eskers stand out as important indicators of former glacial activity, each providing valuable insight into how ice moved and deposited material. Moraines consist of accumulations of debris, including rocks, soil, and unsorted sediments laid down directly by glaciers. They form along the margins of ice masses, marking either the furthest reach of a glacier or points where its movement temporarily paused. Lateral moraines develop along the sides of glaciers as debris carried on the ice surface is deposited, while terminal moraines indicate the maximum advance of the glacier. These formations reveal both the direction of ice movement and periods of stability, helping scientists reconstruct the size and timing of past glacial episodes. Drumlins, in contrast, are smooth, elongated hills made of glacial till that have been molded by flowing ice. Their streamlined, teardrop-like shapes point in the direction of ice movement and reflect the force involved in their formation. Often occurring in groups, drumlins suggest highly dynamic conditions in which ice sheets reshaped underlying sediments, producing landscapes that preserve patterns of glacial flow over time. The alignment and spread of drumlins can provide information about the direction and speed of ice movement during the last glacial maximum. Eskers are winding ridges formed by meltwater streams flowing beneath glaciers. As ice melts, water-carrying sand and gravel travels through tunnels under the glacier, depositing sediment along its course. When the ice finally retreats, these filled channels remain as sinuous ridges on the landscape. Eskers trace the roots of subglacial drainage systems, offering clues about how meltwater moved through or beneath the ice and how glaciers melted from within. Each of these features captures a chapter in the story of glacial movement, deposition, and retreat. By examining moraines, drumlins, and eskers, geologists piece together the history of ice sheets, revealing how they advanced, paused, and eventually withdrew across Earth's surface. Powerful reminders of the role ice has played in shaping the planet's ancient landscapes. Glacial erosion was a decisive force in transforming Earth's surface during the Ice Age, profoundly changing the distribution and nature of lakes and rivers across vast regions. As enormous glaciers advanced and withdrew, their tremendous mass and motion applied intense pressure to the ground below. The scraping effect of rocks and debris frozen into the ice, combined with the relentless grinding against bedrock, gouged deep valleys, fjords, and basins, frequently reshaping existing landforms into newly created water-filled features. Through these actions, a wide range of depressions formed, including cirques, tarns, and kettles, which later filled with meltwater and became countless lakes, many of which remain striking features of the modern landscape. The uneven nature of glacial erosion also strongly influenced how rivers developed and flowed. During periods of advanced glaciers, often blocked river valleys, forming natural dams that redirected watercourses or caused temporary lakes to accumulate upstream. When the ice eventually retreated, these ice dams sometimes failed, suddenly unleashing powerful outburst floods that cut new channels and spread sediments across the land. The aftermath of such events can be seen in distinctive landforms such as streamlined hills and extensive outwash plains, which later guided the paths of rivers. Meltwater from glaciers further reshaped drainage systems by redistributing sediments, laying down gravel, sand, and silt in patterns that determined where rivers could wind, branch, or stabilize. In certain areas, glacial erosion produced broad, gently sloping landscapes dotted with numerous small lakes, a pattern known as kettle lake topography. These lakes typically formed where isolated blocks of ice were buried in glacial deposits and melted gradually over time. The irregular combination of erosion and deposition resulted in a complex mosaic of lakes and waterways shaping local ecosystems and influencing patterns of human settlement. Altogether, the intense erosive strength of glaciers during the Ice Age was central to creating the present-day network of lakes and rivers. Their movement reshaped the land's contours and restructured drainage systems, leaving behind intricate waterways and water-filled basins that continue to influence Earth's surface long after the ice disappeared. Gaining insight into these mechanisms is essential for understanding how ancient ice sheets molded the planet's hydrological features. Scientists rely on a careful and systematic analysis of geological and sedimentary evidence to reconstruct the landscapes of past ice ages, assembling detailed pictures of Earth's ancient environments. A key component of this work involves studying landforms created by glacial processes such as moraines, drumlins, and outwash plains. These structures act as physical records of ice movement, allowing researchers to deduce the size, behavior, and flow patterns of former glaciers. By charting the distribution of these features across large areas, scientists can rebuild the shape of ancient ice sheets and trace their retreat over thousands of years. Sedimentary deposits provide equally valuable information. Layers of glacial till made up of unsorted material laid down directly by ice capture moments of glacier advance and withdrawal. Close stratigraphic examination of these deposits reveals shifts in climate sources of sediment and changes in ice coverage through time. Varves, with their annual layering, offer especially fine detail recording year-by-year variations in temperature, precipitation, and meltwater during the Ice Age. Researchers also study the chemical signatures preserved in sediments to infer past environmental conditions. Isotopic measurements, such as oxygen isotope ratios found in marine and terrestrial deposits, help estimate ancient temperatures and the volume of global ice. These isotopic indicators function as proxies, converting sediment composition into meaningful climate information that feeds into models of ice sheet dynamics. In addition, paleobotanical evidence and microfossils embedded within sediments contribute to landscape reconstructions. Pollen grains and microscopic organisms reveal patterns of vegetation and ecological zones that existed during different stages of glaciation, helping scientists understand both the physical terrain and the climatic conditions that sustained various ecosystems. Modern advances in remote sensing and geochronology have further strengthened these approaches. Methods such as radiocarbon dating and optically stimulated luminescence allow precise age determination of sediment layers, creating a reliable timeline for landscape evolution. Together, these multiple lines of evidence enable scientists to build dynamic reconstructions of Ice Age landscapes, showing how glaciers shaped the terrain and influenced Earth's surface over tens of thousands of years. This process of reconstruction forms a vital basis for understanding how the legacy of ancient ice continues to shape the world we inhabit today. The lasting mark left by glacial landscapes continues to shape modern geography in deep and varied ways. As glaciers advanced and withdrew over tens of thousands of years, they carved and reshaped the Earth's surface, producing features that remain long after the ice itself disappeared. These landforms act as tangible records of ancient climatic changes, while also influencing present-day ecosystems, human activity, and patterns of land use. Among the most significant long-term consequences of glacial processes is the creation of distinctive features such as U-shaped valleys, fjords, and moraines. U-shaped valleys formed as massive ice sheets slowly ground their way through mountain terrain, still stand out as defining elements of many alpine regions. Fjords, which are deep coastal inlets carved by glaciers and later flooded by the sea, are especially prominent in places like Norway and New Zealand, where they create unique habitats and influence local climate conditions. Moraines made up of rock sediment and debris deposited by retreating glaciers often form fertile landscapes and natural groundwater reservoirs, shaping agricultural development and settlement patterns across many areas. Glacial erosion and deposition have also played a major role in reshaping drainage networks and the distribution of sediments. As material was transported and redeposited, vast alluvial plains and deltaic systems formed altering river pathways and coastal environments. These sediment deposits affect soil richness, guiding farming practices and supporting diverse forms of life. Some of the most persistent changes occurred within the Earth's crust itself. The immense weight of glaciers pushed the land downward, creating isostatic depression. When the ice melted and retreated, the land slowly rose again through a process known as isostatic rebound, gradually modifying local landscapes and generating new landforms. In certain coastal regions, this uplift raised former seabeds above sea level, reshaping shorelines and influencing ocean current patterns. The influence of glacial landscapes goes beyond their physical structures. These features help regulate local climates, as valleys and glacial lakes can shape regional microclimates. In many parts of the world, remnants of Ice Age glaciers still provide essential freshwater supplies, supporting ecosystems and human societies alike. As evidence of their enduring impact, glacial legacies remain woven into the structure of Earth's surface, continuing to shape the environment long after the ice has vanished. As glaciers pulled back from continental landmasses, their withdrawal left landscapes permanently transformed, with coastlines displaying clear signs of this immense change. The melting of these enormous ice sheets did more than uncover new terrain. It actively molded modern coastlines through combined processes of erosion and deposition. As the tremendous weight of ice was removed, the Earth's crust gradually rebounded through isostatic uplift, slowly raising former glacier beds and altering coastal elevations over thousands of years. At the same time, retreating glaciers released vast amounts of meltwater that flooded low-lying areas, forming inland seas and fjords. These deep glacially carved inlets became defining features of regions such as Scandinavia, New Zealand, and parts of North America. Glacial erosion shaped U-shaped valleys and steep fjord walls, which once submerged produced some of the most dramatic coastlines on the planet. These flooded glacial valleys not only determined the shape of the land, but also affected ocean circulation patterns and marine ecosystems. Sediment deposition was equally important. As glaciers receded, they left behind mixtures of till, gravel and silt along coastal margins, forming moraines and drumlins that sometimes extended into marine environments. Over time, waves and tides reworked these materials, giving rise to barrier islands, deltas, and estuaries that characterize many post-glacial coastlines today. These environments often support rich biodiversity, demonstrating how Ice Age processes continue to shape ecological systems. The combined effects of glacial erosion, isostatic adjustment, and sediment deposition produced coastlines marked by complex forms, including fjords, estuaries, and barrier islands that define many of Earth's most recognizable shores. These landscapes stand as lasting reminders of the immense power of ice and the dynamic forces that continue to mold the planet's surface long after the glaciers themselves have disappeared. Understanding how Ice Age glaciers shaped coastlines offers valuable insight into ongoing geological processes and the continually evolving nature of Earth's boundaries. Permafrost and periglacial processes have played a powerful role in shaping the landscapes of Earth's cold regions, leaving behind effects that continue to influence these environments long after the height of glaciation. Permafrost, defined as ground that remains permanently frozen, forms a critical foundation in polar and subpolar areas, influencing both what happens on the surface and what occurs below it. Its presence helps stabilize soil and rock, limiting extensive erosion. Yet, it also gives rise to distinctive landforms such as patterned ground pingos and thermokarst terrain. These features develop through repeated cycles of freezing and thawing processes that gradually break apart and reorganize the landscape over thousands of years. Periglacial processes, which are closely associated with the existence of permafrost, are responsible for producing a wide range of characteristic landforms. One example is frost, heaving the upward displacement of soil and rock caused by the expansion of water as it freezes, which leads to the formation of patterned ground, including sorted circles and stripes. These striking patterns reflect the constant interaction between ice-rich soils and seasonal temperature changes. In areas where permafrost becomes vulnerable to thawing, thermokarst landscapes emerge marked by uneven ground depressions, sinkholes, and surface collapse resulting from subsidence. These features not only reshape the physical terrain, but also strongly influence hydrology, creating lakes, ponds, and wetlands that serve as important habitats. The extent and stability of permafrost are closely tied to climate, with colder phases during the Ice Age, encouraging widespread permafrost development. As temperatures fluctuated, periglacial processes intensified, carving intricate surface patterns and affecting the movement of sediments. These dynamics also drove the redistribution of sediments and organic matter, with significant consequences for local ecosystems and carbon cycling. When the climate warmed toward the end of the last Ice Age, permafrost began to thaw, releasing stored greenhouse gases and dramatically transforming the landscape. The influence of permafrost and periglacial processes reveals a terrain in constant change, molded by shifting climate conditions and the ongoing interactions between ice, soil, and water. Their lasting imprint offers valuable insight into how Earth's surface responds to repeated freezing and thawing, setting the foundation for understanding the climatic transitions that mark the close of the last Ice Age and the move toward a warmer world. The conclusion of the last Ice Age was signaled by a sequence of deep and complex climatic changes that reshaped Earth's surface and altered atmospheric conditions. As the planet slowly warmed, these transformations were driven by a combination of factors that disrupted the fragile balance sustaining glacial conditions. At the heart of this transition was a notable rise in global temperatures, which triggered the melting of massive ice sheets that had covered large portions of North America, Eurasia, and other regions. This warming did not occur evenly, but resulted from the combined effects of reduced ice albedo feedback changes in atmospheric greenhouse gas concentrations and shifts in both oceanic and atmospheric circulation. One of the most important climatic developments involved the redistribution of heat across the planet. As ice sheets shrank, reflective ice surfaces were replaced by darker land and open water, which absorbed more solar radiation and reinforced the warming trend. At the same time, variations in greenhouse gases such as carbon dioxide and methane, released in part from thawing permafrost and ocean sources, further intensified the warming. These gases trap heat within the atmosphere, strengthening the greenhouse effect and speeding up ice melt. Volcanic activity, although occurring intermittently, also influenced atmospheric composition, sometimes producing short-term cooling, but generally playing a smaller role compared to greenhouse gases. Shifts in ocean currents and atmospheric circulation were also crucial in bringing Ice Age conditions to an end. Melting ice altered ocean salinity and stratification, which then affected the strength and pathways of major currents responsible for distributing heat around the globe. These changes helped sustain a warmer climate by moving heat more efficiently toward both the poles and the equator than during glacial times. The withdrawal of ice sheets also caused major reductions in surface albedo, exposing darker land and ocean surfaces that absorbed additional sunlight. This positive feedback loop accelerated warming even further. As the ice receded, landscapes were transformed, opening new routes for migration and creating new habitats, while also laying the groundwork for rising sea levels. Gaining insight into these climatic shifts helps explain the profound transition from the frozen environment of the last ice age to the comparatively warm and stable climate experienced today. This transition not only reshaped the surface of the Earth, but also laid the groundwork for the complex interactions between climate, sea levels and coastlines that continue to shape our planet today, as the immense ice sheets that once covered much of the northern hemisphere began their gradual withdrawal. Their impact extended far beyond simple changes to the landscape. As these enormous bodies of ice melted, global sea levels rose substantially, a process that dramatically altered coastlines and transformed entire continents. During glacial periods, vast quantities of water were locked within ice sheets, causing sea levels to fall as the oceans effectively shrank. When warming conditions triggered the retreat of the ice, this stored water flowed back into the oceans, producing a series of rapid and often striking increases in sea level. These rising seas had immediate and widespread consequences for coastal regions around the world. Low-lying areas that had once been exposed or bordered by ice were converted into broad, shallow seas or productive coastal plains. Certain landforms, including extensive continental shelves, were revealed during glacial maxima, only to be submerged again during interglacial phases. Such repeated shifts generated a highly dynamic and ever-changing shoreline, shaping patterns of sediment deposition and erosion, and influencing the distribution of ecosystems. The flooding of coastal zones also had major effects on both human and animal populations. As shorelines advanced and retreated, habitats were drowned or newly exposed, compelling species to adapt, migrate, or face extinction. For early human populations, these changes could provide access to new resources or result in the loss of long-established hunting areas. In marine environments, alterations in water depth and salinity gradients affected nutrient distribution and supported the development of diverse marine communities. The retreating ice sheets further contributed to changes in freshwater distribution and modifications to ocean circulation. As huge volumes of meltwater entered the oceans, established current systems could be temporarily disrupted, influencing global climate patterns. These changes affected regional weather systems and played a role in stabilizing or destabilizing later climate cycles. Overall, the melting of ice sheets during deglaciation acted as a powerful force in transforming sea levels and coastlines, initiating long-term ecological and geological changes that continue to influence the Earth's surface long after the ice itself disappeared. As the climate shifted from glacial to interglacial conditions, the environment experienced profound changes that reshaped the planet's ecological framework. This transition, driven by subtle adjustments in Earth's orbit and atmospheric composition, set off a cascade of environmental and ecological effects. As glaciers withdrew, vast new habitats were revealed, altering physical geography and creating opportunities for a wide range of ecosystems to develop. One of the most significant transformations involved the redistribution of water. The melting ice led to rising sea levels, flooding low-lying coastal regions and modifying ocean circulation patterns. These changes affected temperature and salinity gradients, which in turn influenced the distribution and productivity of marine life. The movement of fresh water also altered river systems, opening new channels and modifying sediment transport, which encouraged the formation of fertile floodplains and wetlands. These environments became centers of plant growth, supporting a rapid increase in terrestrial biodiversity. As ice sheets retreated previously, glaciated landscapes were exposed, allowing pioneer species such as resilient grasses and shrubs to take hold on newly available ground. These early colonizers prepared the way for more complex ecosystems, drawing in herbivores and predators. The expansion of plant life provided essential energy resources, supporting the growth of herbivorous mammals and driving changes in food webs. As temperatures and rainfall patterns became more stable, forests re-established themselves across many regions, forming dense habitats capable of sustaining a wide variety of species. From an ecological perspective, this period represented a critical shift toward increased biodiversity. Species adapted to colder climates either moved northward or survived in refugia, while others developed traits better suited to warmer conditions. The evolving climate imposed new evolutionary pressures, leading to both speciation and extinction and reshaping biological communities. These interacting processes helped create a new balance, laying the foundation for the complex ecosystems characteristic of modern interglacial periods. Understanding these environmental and ecological consequences emphasizes the deep interconnection between climate and life. The shift from a world of ice to one of increasing warmth did more than alter the shape of the land. It transformed the relationships between species, ecosystems, and the planet as a whole. This complex process of change laid the foundations for the biological diversity we observe today and encourages reflection on how modern climate changes may likewise shape Earth's future. As the icy hold of the last ice age loosened plants and animals encountered environments rapidly reshaped by intense and far-reaching climatic changes. Species that had flourished in cold, severe conditions were forced to adapt swiftly or disappear. Many plant species responded by migrating, moving toward regions with more suitable climates. For example, tundra vegetation gradually shifted northward as ice sheets retreated, forming new ecosystems in areas that had once been uninhabitable. These migrating plant communities often became the base of newly forming ecosystems, sustaining herbivores, and in turn, the predators that followed them. Animals reacted to the warming world in varied ways. Large megafauna, such as mammoths, woolly rhinoceroses, and saber-toothed cats, were increasingly confined to isolated refugia, as their broad habitats diminished. Some survived for a time in cold, high-altitude or northern regions, but many ultimately faced extinction due to the rapid speed of environmental change combined with growing human pressure. Smaller and more flexible species, including deer elk and numerous rodents, expanded their ranges, taking advantage of newly available plant life and open terrain. Birds, many of which depend heavily on migration, adjusted both the timing and routes of their journeys to match changes in plant growth cycles, ensuring continued access to food during breeding and migration periods. The conclusion of the Ice Age triggered a chain of ecological transformations. As glaciers melted, vast amounts of fresh water flowed into the oceans, altering salinity levels and ocean currents, which in turn reshaped marine ecosystems. Fish populations shifted to new spawning areas, while marine mammals expanded into coastlines that had previously been inaccessible. In many regions, forests replaced tundra, creating more complex habitats capable of supporting a wider range of species. These sweeping environmental changes generated evolutionary pressures that encouraged adaptation, and in some cases, the emergence of new species. The varied responses of plants and animals during this period highlight the resilience and flexibility of life, even as the rapid pace of change placed immense strain on many species, leading to extinctions and large-scale migrations that permanently shaped the living world of post-Ice Age Earth. The close interaction between climatic change and biological response illustrates the powerful role environmental forces play in guiding the evolution of life. As the Ice Age came to an end, human activity emerged as an increasingly important influence on the changing landscapes and ecosystems of the former glacial world. Early humans, using simple tools and adaptable survival strategies, began to affect their surroundings in ways that would leave long-lasting marks. Although their initial impact was modest, mainly through hunting-gathering and movement across the land, these actions gradually reshaped environments and set the stage for the later rise of agriculture and permanent settlements. One of the most significant human influences on post-Ice Age ecosystems was the extinction of megafauna. As human groups spread into new regions, hunting contributed to the decline and eventual loss of large animals such as mammoths and saber-toothed cats. The disappearance of these key species disrupted ecological balances, altering vegetation patterns and nutrient cycles. Without these animals, plant communities changed dramatically, reshaping the structure and composition of emerging forests and grasslands. The development of agriculture marked a major turning point in human-environment interaction, as societies shifted from nomadic lifestyles to settled farming. People began deliberately reshaping the land. Forests were cleared for crops, irrigation systems were built, and plants and animals were domesticated, accelerating environmental change. These practices increased soil erosion, modified local water systems, and introduced new species that often competed with native plants and animals. In later periods, urban growth and widespread deforestation further transformed landscapes. Expanding populations required more space, leading to habitat fragmentation and the loss of natural ecosystems. This expanding human footprint also contributed to climate feedback processes, including increased greenhouse gas emissions linked to land use changes, which in turn influenced climate patterns and the rate of environmental transformation. Overall, human activity became an ever more powerful force in the post-Ice Age world, shifting from a largely passive presence to an active driver of ecological change. Early human actions laid the foundations for the complex and enduring relationships between humanity and the environment that continue to shape the planet today. Acknowledging this influence allows us to better understand the deeply rooted link between human development and environmental change, a connection that remains essential for interpreting both past and future climate dynamics. To determine the timing and sequence of Ice Age endings, scientists rely on a range of advanced dating approaches, drawn from geochronology and paleoclimatology. Among the most important of these is radiocarbon dating, a method that tracks the decay of carbon-14 in organic materials and is effective for samples up to about 50,000 years old. When analyzing ice cores, sediments, or fossilized remains, radiocarbon dating offers accurate age estimates for relatively recent changes, such as the close of the last glacial period. For older events that extend beyond the limits of radiocarbon dating, researchers instead depend on isotope ratio studies, particularly those involving oxygen isotopes 16O and 18O. The proportion of these isotopes preserved in ice cores and marine sediments acts as a powerful indicator of ancient temperatures and global ice volume. Shifts in oxygen isotope ratios provide detailed information about the timing of ice sheet expansion and melting, enabling scientists to identify when glaciers advanced or retreated with impressive precision. Another essential method involves studying layered sediments and ice cores, which often retain annual or even seasonal records. Changes in dust content volcanic ash layers and trapped gas bubbles within these layers serve as chronological markers. Volcanic ash layers, or tephra for example, function as time markers that can be traced across multiple locations, allowing ice core data to be linked to broader global events. In addition, scientists apply astronomical tuning, also called orbital tuning, which aligns climate proxy records with calculated variations in Earth's orbital characteristics, including eccentricity, obliquity, and precession. by matching repeating patterns in climate indicators to known orbital cycles. Researchers can fine-tune the timing of deglaciation with great accuracy, building a detailed picture of how ice sheets responded to changes in Earth's orbit. When combined, these techniques form a comprehensive framework for interpreting the complex processes involved in Ice Age terminations. They reveal not only approximate dates for glacial retreat, but also the subtle pace and order of environmental changes, shedding light on whether these transitions occurred gradually or through abrupt shifts driven by evolving climate forces. The issue of whether Ice Age endings happened suddenly or unfolded slowly over long periods has long captured scientific interest, prompting a range of hypotheses based on paleoclimate evidence. Recent findings indicate that the shift from glacial to interglacial conditions often reflected a complex mix of rapid changes and slower developments, challenging earlier views of a purely gradual transition. One influential idea suggests that certain abrupt climate events, such as the Berling-Allerud warming around 14,700 years ago, took place over just decades to centuries, implying that some aspects of Ice Age termination could occur very quickly. These rapid warmings are frequently linked to sudden releases of greenhouse gases, especially methane from thawing permafrost and subglacial lakes, which intensified warming and sped up ice loss. Such feedback processes may have triggered tipping points, causing the climate system to shift rapidly from glacial to interglacial conditions. In contrast, other lines of evidence point to a more gradual transition, driven by slow but continuous changes in Earth's orbital parameters, ocean circulation patterns, and greenhouse gas levels. Over thousands of years, these influences altered solar radiation patterns and sea levels, progressively reducing the size of ice sheets. The interaction between steady background forces and episodic abrupt events produced a varied pattern of change, with some intervals marked by rapid climate swings and others defined by long periods of gradual adjustment. Advances in ice core and sediment research have shown that the conclusion of past ice ages was not a single uniform event, but rather a sequence of oscillations, punctuated by brief warming episodes that eventually led to a relatively stable interglacial phase. This refined understanding highlights the complexity of climate system responses, which involve both sudden thresholds and incremental shifts. Recognizing these patterns not only deepens insight into past climate behavior, but also helps improve models that predict how present and future climate systems may respond to ongoing human influence. By studying the processes that brought previous ice ages to an end, scientists gain valuable insight into the mechanisms behind large-scale climate change. These historical transitions demonstrate how Earth's climate responds to intricate interactions among atmospheric composition, ocean processes, and land-based feedbacks. For instance, the abrupt warming episodes known as Dansgaard-Oeschger cycles, which occur during deglaciation phases, illustrate the potential for rapid climate change driven by internal feedback loops within the climate system. Understanding these events shows how relatively small initial disturbances, such as changes in greenhouse gas concentrations or shifts in ocean circulation, can set off rapid and far-reaching rises in temperature. Reconstructing both the timing and speed of past deglaciations has also clarified the importance of ice sheet behavior and the mechanisms that regulate climate. As ice sheets melted and retreated, they affected global sea levels, changed Earth's albedo, and disturbed ocean currents responsible for moving heat around the planet. These feedback processes frequently intensified warming, driving additional melting and increasing climate instability. Identifying the thresholds and tipping points that allowed these transitions to occur helps scientists recognize comparable weaknesses within the modern climate system. In addition, paleoclimate records highlight the significance of ocean-atmosphere interactions, especially the influence of ocean circulation systems, such as the Atlantic meridional overturning circulation, in controlling climate during periods of deglaciation. Variations in fresh water input from melting ice altered salinity and density-driven currents, leading to changes in heat transport that sped up warming phases. These findings stress the interconnected nature of Earth's systems and show how disruption in one component can trigger widespread climatic consequences. By examining how previous ice ages ended, researchers refine models that more accurately represent possible future outcomes. Such models include the feedback's thresholds and response times observed in the past, supporting policymakers as they assess the dangers of rapid climate change today. Ultimately, insights drawn from Earth's climatic history act as an essential guide, shaping predictions and responses as society faces the ongoing challenges of climate change. During the vast climatic transformations of the Ice Age, the world's oceans were far from unchanged, instead undergoing major shifts in salinity temperature and circulation patterns. As glaciers advanced and enormous ice sheets stored water on land, sea levels declined, revealing continental shelves and interrupting long-established currents. These changes produced cascading effects on ocean properties, reshaping marine environments in ways that reverberated throughout global systems. The buildup of ice effectively removed large volumes of fresh water from the oceans, increasing salinity in regions where evaporation surpassed precipitation, while other areas became more diluted. This uneven salinity distribution influenced seawater density, which in turn altered thermohaline circulation. The global conveyor belt that redistributes heat and nutrients across the planet illustrates this process as in the North Atlantic. Greater freshwater input from melting ice during deglaciation phases temporarily weakened these currents, prompting climate shifts at both regional and global scales. Ocean temperature changes were closely linked to ice sheet dynamics, with colder surface waters forming near expanded ice-covered zones. These cold waters often reinforced sea ice formation, further insulating the ocean and limiting heat exchange with the atmosphere. In contrast, during warmer interstadial intervals, melting ice sheets released enormous amounts of fresh water into the oceans, disturbing established temperature gradients and circulation routes. The reorganization of circulation patterns during glacial periods had wide-ranging effects on nutrient transport, marine ecosystems, and climate regulation. Altered currents could isolate or reconnect different ocean basins, changing the exchange of heat and salinity across the globe. These shifts in ocean dynamics were central to either amplifying or restraining ice sheet growth, generating feedback loops that prolonged or reversed glacial expansion. Grasping these intricate interactions highlights the critical role of ocean responses during the Ice Age. Their impact went beyond simple climate moderation, fundamentally reshaping the chemistry and movement of the world's oceans, leaving a lasting imprint still evident today in submerged landscapes and geological records that preserve evidence of these dramatic changes. Submerged landscapes offer a striking glimpse into the pronounced sea level variations that defined Ice Age intervals. During these colder phases, immense quantities of water were trapped within extensive ice sheets, causing global sea levels to fall dramatically at times by as much as 120 meters below present-day levels. This substantial drop in sea level exposed continental shelves that are now underwater, forming land bridges and expansive coastal plains that were once accessible to early human populations and migrating animals. The tangible traces of these transformations are clearly visible in submerged landscapes uncovered through marine geology and high-resolution sonar mapping. Underwater terraces, for example, identify ancient coastlines, while flooded river channels, known as paleovalleys, map the courses once cut by flowing fresh water before rising seas covered them. The North Sea, as one illustration, preserves vast underwater terrains that once functioned as land routes, showing how lower sea levels created corridors that enabled migration across Europe and Asia. In a similar way, submerged terraces along the Atlantic shores of North America and Europe indicate earlier shoreline positions, confirming the magnitude of past sea level changes. Coral reefs and drowned coastal features also provide essential clues. During times of reduced sea level, many reefs developed on landforms that are now submerged, and their fossil remains preserved beneath the ocean offer clear snapshots of sea level at particular moments in time. Sediment cores taken from these underwater regions further document variations in water depth and climate, supplying detailed chronological records of sea level change. When combined with radiocarbon dating of organic material recovered from submerged deposits, these findings allow scientists to reconstruct sea level timelines with impressive accuracy. Evidence from these submerged landscapes is crucial not only for interpreting ancient sea level behavior, but also for highlighting the sweeping effects of Ice Age climate shifts on Earth's surface. As ice sheets advanced and withdrew, coastlines and land-sea boundaries were repeatedly reshaped, leaving behind an underwater record of a world in continual transition. Such discoveries deepen our understanding of how climatic oscillations have historically molded the planet's geography, laying the groundwork for human migrations and ecological change. The appearance of land bridges such as Beringia had a profound influence on migration patterns and species dispersal throughout the Ice Age. As enormous ice sheets grew and receded, sea levels shifted dramatically, at times falling by as much as 120 meters below present levels, revealing extensive areas of continental shelf. These newly exposed land connections formed routes that were submerged during interglacial periods, effectively redefining the geography of the Northern Hemisphere. Beringia, linking Asia and North America, stands as a clear example of how such bridges became crucial passageways for both animals and humans. When sea levels were low, large mammals, including mammoths, bison, and camels, crossed these corridors, taking advantage of the rich resources of the expanding tundra. Human groups, likely tracking migrating herds, also used Beringia, enabling one of the earliest known movements of people into the Americas. These journeys were not simply the relocation of individual species, but part of complex ecological exchanges that promoted genetic mixing and the spread of plants and animals between continents. The availability of land bridges also drove important evolutionary processes. Populations isolated by ice sheets and oceans during interglacial phases diverged over time, evolving independently and increasing regional diversity. In contrast, during glacial maxima, cold-adapted species rapidly expanded into new areas, sometimes giving rise to specialized subspecies or even entirely new species as habitats fragmented and shifted. Beyond guiding migration, land bridges shaped ecological relationships and interactions between continents. They allowed not only the movement of species, but also the transmission of pathogens and the development of symbiotic connections, creating a complex network of biological exchange. When ice sheets melted and sea levels rose once more, these routes disappeared beneath the water, confining species to newly occupied and often isolated environments and setting the course for future evolutionary paths. Reflecting on how these land bridges controlled migration patterns makes it clear that their formation played a decisive role in the biological and cultural changes of the Ice Age world. This consideration naturally leads to questions about how alterations in ocean circulation further transformed the global climate during these highly dynamic periods. Shifts in ocean currents during the Ice Age had a major impact on global climate by redistributing heat across the Earth's surface. As ice sheets expanded and contracted, they changed the arrangement of land masses and the shape of ocean basins, which in turn adjusted the routes and intensity of major currents such as the Gulf Stream and the Antarctic Circumpolar Current. These adjustments triggered cascading effects throughout the climate system, particularly in areas far removed from the ice sheets themselves. During glacial phases, the accumulation of enormous ice sheets in the northern hemisphere interfered with the normal movement of warm equatorial waters toward higher latitudes. This disruption often weakened or redirected the Gulf Stream, reducing the transport of heat from the tropics to northern Europe and North America. The diminished delivery of warmth helped sustain the colder, more stable conditions that define an ice age. In certain regions, however, altered current pathways strengthened cold surface waters, encouraging the spread of sea ice and intensifying regional cooling. The rearrangement of oceanic heat also affected the strength and position of thermohaline circulation, the planet's global conveyor belt driven by contrasts in water density. During colder intervals, increased sea ice formation and the addition of fresh water from melting glaciers could interfere with this circulation, creating a bottleneck that slowed the transfer of heat across the oceans. This reduction in flow reinforced cooling trends, forming a feedback loop that helped preserve frigid conditions. When the climate later warmed and glaciers retreated, freshwater input declined, enabling thermohaline circulation to regain strength, spread heat more evenly, and moderate global cooling. These changes in ocean currents influenced not only temperature regulation, but also the distribution and intensity of storms, monsoon systems, and precipitation patterns. Such alterations could spark widespread ecological and atmospheric shifts, affecting the stability of ice sheets and the global climate system overall. As researchers continued to disentangle the intricate relationship between ocean currents and climate during the Ice Age, it became evident that these immense dynamic flows were central to shaping Earth's climatic past. This realization naturally raises questions about how freshwater inputs, especially from icebergs, later affected ocean circulation and climate stability. Icebergs and freshwater input had profound impacts on ocean circulation and climate systems throughout the Ice Age, influencing the broader environment in complex and far-reaching ways. Vast icebergs carved from expanding ice sheets frequently drifted into ocean basins, releasing large volumes of fresh water into marine environments. These episodic surges of fresh water were capable of disturbing established ocean currents, particularly thermohaline circulation, which depends on differences in water density shaped by temperature and salinity. When substantial amounts of fresh water entered the North Atlantic and other critical ocean gateways, seawater salinity was diluted, lowering its density and hindering the sinking of cold, dense water that normally drives deep ocean currents. This interference could weaken the Atlantic meridional overturning circulation, resulting in pronounced regional cooling due to reduced heat transport from equatorial regions. Such freshwater pulses often aligned with sudden climate fluctuations known as Dansgaard-Oeschger events, marked by rapid warming followed by cooling episodes within broader glacial intervals. Beyond immediate temperature effects, freshwater influx also influenced the extent and stability of sea ice. Increased freshwater input could encourage sea ice expansion, further insulating the ocean from the atmosphere and amplifying cooling effects. In contrast, periods with reduced freshwater input frequently corresponded with warmer interstadial phases, allowing robust ocean circulation to re-establish and redistribute heat on a global scale. The influence of fresh water and icebergs extended well beyond regional impacts. They played a key role in the cyclical nature of climate variability during the Ice Age. Fluctuations in iceberg carving and meltwater release were closely tied to the growth and decay of ice sheets, creating feedback mechanisms that shaped not only local environments but global climate patterns as well. Understanding these processes requires examining how episodic freshwater forcing altered the delicate balance between oceanic and atmospheric systems, laying the groundwork for how scientists interpret ancient climate records using sediment and isotopic evidence. To uncover the conditions of past oceans during the Ice Age, scientists rely on a range of innovative approaches centered on sediment cores and isotopic analysis. These techniques function as natural archives, preserving extensive information that enables researchers to reconstruct climate variability and ocean behavior with impressive accuracy. Sediment cores recovered from the ocean floor serve as time capsules made up of layered deposits that accumulated gradually over thousands of years. As particles descend through the water column, they transport with them clear indicators of the environmental conditions present at the moment they were deposited, including mineral composition, organic matter, and microscopic fossils. By studying the makeup and stratified arrangement of these sediments, scientists are able to deduce shifts in ocean productivity changes in circulation patterns and even variations in the extent of ice coverage. For example, differences in the types and quantities of microfossils can signal alterations in nutrient supply and water temperature, allowing researchers to construct a detailed reconstruction of ancient ocean environments. Alongside sediment studies, isotopic analysis investigates the chemical fingerprints preserved within these layers. Stable oxygen isotopes, especially oxygen 18-18O and oxygen 16-16O, are particularly revealing. The proportion of these isotopes found in the calcium carbonate shells of marine microfossils reflects both the temperature of the oceans and the size of global ice sheets at the time the organisms lived. In colder climates, greater amounts of 16O become trapped within expanding ice sheets, leaving seawater relatively enriched in 18O. When scientists analyze these fossil shells, they can trace changes in global ice volume and temperature over time. In a similar way, isotopic patterns of carbon and other elements offer valuable information about ocean productivity and the cycling of carbon processes that are tightly connected to climatic transitions. By integrating sediment layering with isotopic evidence, researchers can assemble precise timelines of ocean temperature variation, sea level change, and circulation shifts across multiple ice age phases. These reconstructions not only enhance our understanding of ancient climate systems, but also act as important reference points for interpreting modern changes in the oceans and atmosphere, helping to clarify how Earth responds to ongoing climate variability. As scientific methods continue to advance, the combined use of these approaches steadily improves our understanding of the complex interactions that have shaped the planet's climatic past. The dramatic transformations in ocean conditions during the Ice Age provide essential insight into the processes that drive climate variability today. Throughout glacial periods, major drops in sea level, often exceeding 100 meters, redefined coastlines and changed how heat and nutrients were distributed within marine environments. Such alterations disrupted long-established ocean circulation systems, particularly the thermohaline conveyor belt, which is crucial for regulating global climate through the movement of warm and cold water masses. Data drawn from sediment cores show that periods of strengthening or weakening in these currents closely aligned with climate changes, underlining their sensitivity to variations in ice sheet size and freshwater input, resulting from ice growth or melting. The repeated advance and retreat of massive ice sheets also affected salinity and temperature gradients in both the North Atlantic and the Southern Oceans, shaping the strength and reliability of major ocean pathways. These circulation changes contributed to episodes of rapid climate transition, with certain regions undergoing sudden cooling or warming, depending on how heat transport was altered. Examining these historical ocean responses helps clarify the feedback relationships linking ice sheets, ocean currents, and atmospheric conditions, highlighting the deeply interconnected nature of Earth's climate system. In addition, the melting of ice sheets during deglaciation released enormous volumes of fresh water into the oceans, frequently destabilizing circulation patterns and triggering widespread climatic shifts. These past events serve as valuable modern comparisons for understanding how future freshwater influxes driven by accelerated ice melt could disrupt existing ocean circulation and potentially lead to abrupt climate changes. The significance of these findings goes far beyond historical interest. They emphasize the critical role of ocean stability in sustaining climate balance. Understanding how earlier ocean changes influenced climate variability improves our capacity to interpret present-day developments such as the weakening of the Atlantic meridional overturning circulation, which may have extensive regional and global consequences. As scientists continue to unravel these ancient oceanic behaviors, the lessons they offer remain essential for anticipating and reducing the impacts of future climate change, reinforcing the ocean's central role in maintaining Earth's climate resilience. During the intense and often unpredictable climate fluctuations of the Ice Age, marine organisms encountered both severe challenges and unique opportunities for adaptation. As glaciers repeatedly expanded and retreated, sea levels rose and fell, dramatically reshaping coastlines and transforming marine habitats. These shifts compelled marine life to adopt a wide range of survival strategies. Many species undertook extensive migrations to stay within suitable temperature ranges, frequently moving from lower latitude tropical waters toward cooler northern or southern regions as ice sheets advanced. In contrast, during phases of ice retreat, some species broadened their distribution, spreading into newly revealed continental shelves and shallow marine environments created by lower sea levels. Physiological adaptations also proved to be essential for survival. Species adapted to cold environments developed thicker forms of insulation, such as blubber in marine mammals and denser shells in mollusks, enabling them to endure much lower temperatures. Certain plankton communities, which form the base of marine food webs, evolved to flourish under shifting nutrient conditions linked to changing ocean currents and expanding ice cover. The development of seasonal polyneous areas of open water surrounded by sea ice became especially important as feeding and breeding grounds, sustaining diverse ecosystems despite the surrounding ice. The constantly changing extent of ice sheets affected not only where marine species could persist, but also how they interacted within their ecosystems. As ice withdrew, newly exposed habitats appeared encouraging rapid colonization by both benthic and pelagic organisms. In some situations, isolated populations adjusted to very specific conditions, eventually giving rise to new species. In contrast, during periods of widespread glaciation, the reduction of open water limited movement and genetic exchange, leading to population bottlenecks and localized extinctions. The ability of marine life to endure these fluctuating conditions highlights the close connection between climate dynamics and biological adaptation. Patterns of migration, physiological change, and ecological transformation have left clear signatures in the fossil record, providing crucial evidence of past environmental states. Learning how marine organisms responded to Ice Age variability not only sheds light on the history of life on Earth, but also improves our capacity to anticipate how modern climate change may affect marine ecosystems. As we explore the techniques scientists use to uncover these ancient narratives, it becomes evident that understanding the past is fundamental to interpreting the future of the planet's icy and oceanic realms. Deciphering the story of Earth's frozen past depends on a range of advanced dating methods that allow researchers to determine accurate ages for sediments and fossils from Ice Age periods. At the heart of this work are techniques that examine physical, chemical, and isotopic characteristics of samples, each contributing distinct insights into the timing of glacial events and the organisms that lived through them. Among the most important approaches is radiometric dating, which measures the decay of naturally occurring isotopes within minerals. For instance, uranium series dating can be applied to calcium carbonate formations, such as cave stalagmites, yielding age estimates that span hundreds of thousands of years. In a similar way, potassium-argon and argon-argon methods are used to date volcanic ash layers embedded in sediments. These tephra layers serve as precise chronological markers, helping scientists constrain the ages of nearby sediments and fossils. Alongside radiometric techniques, biostratigraphy and paleomagnetic dating provide additional tools. Biostratigraphy relies on identifying and correlating fossil assemblages, including pollen microfossils or animal remains, whose evolutionary timelines are well understood. By comparing fossil records from different locations, scientists can estimate relative ages and trace patterns of migration. Paleomagnetic dating focuses on reversals in Earth's magnetic field that are preserved in rocks and sediments. Because these geomagnetic reversals occurred simultaneously worldwide, recognizing them within sediment layers offers a reliable chronological framework. Another important method is luminescence dating, which includes optically stimulated luminescence and thermoluminescence. These techniques measure the buildup of trapped electrons in mineral grains that have been exposed to sunlight or heat. Once sediments are buried, this trapped energy accumulates at a predictable rate, allowing researchers to calculate how much time has passed since the grains were last exposed to light or heat. Together, these approaches generate a detailed timeline for Ice Age sediments and fossils. By combining multiple dating methods, scientists can construct a refined chronology of glacial advances, retreats, and related biological changes. This integrated framework forms the foundation for understanding the complex dynamics of Earth's Ice Age history, revealing clues about past atmospheric and climatic conditions, and naturally leading into how ice cores preserve the stories locked within ancient polar archives. Ice cores are extraordinary records of Earth's climatic past, providing an unmatched glimpse into ancient atmospheres and environmental conditions extracted from ice sheets and glaciers. These cylindrical samples preserve a layered timeline extending back hundreds of thousands of years. As snow accumulates annually, each layer becomes a snapshot in time, capturing the composition of the atmosphere at the moment it formed. Unlocking this information depends on analyzing the tiny air bubbles trapped within the ice. When snow falls, small pockets of air are sealed in as the snow compresses into solid ice. Over thousands of years, these trapped bubbles preserve momentary records of the ancient atmosphere, including levels of greenhouse gases such as carbon dioxide and methane. By measuring how the concentrations of these gases change from one ice layer to another, scientists can trace shifts in Earth's climate, revealing clear patterns of warming and cooling. For example, higher amounts of greenhouse gases are commonly associated with warmer interglacial periods, while lower concentrations tend to coincide with Ice Age conditions. Ice cores hold far more than gases alone. They also contain a rich archive of additional climate indicators. Tiny particles such as volcanic ash or wind-blown dust can become locked within the ice, pointing to past volcanic events or changes in atmospheric circulation. Isotopic studies, especially those involving oxygen and hydrogen, provide valuable clues about historical temperatures. Lighter isotopes evaporate more easily during warmer phases, creating distinctive isotopic patterns that allow researchers to reconstruct temperature changes across long spans of time. The layered structure of ice cores further enables scientists to build highly detailed timelines. By counting annual layers, much like tree rings, they can establish accurate chronologies. This precise dating makes it possible to link climate transitions with other paleo-environmental evidence, deepening our understanding of how Earth's climate systems have changed. Continued advances in ice core research are sharpening our picture of past climates, uncovering intricate relationships among atmospheric composition, temperature, and Earth's orbital characteristics. As researchers decode these frozen layers, they gain vital insights into natural climate variability and possible future climate pathways. Careful study of the fine details preserved in ice cores underpins broader explorations of Earth's ever-changing climate history, connecting past, present, and future within a single ongoing story. Scientists who study glacial landforms rely on a blend of detailed field observations, advanced imaging technologies, and geochronological methods to reconstruct ancient ice movements with impressive accuracy. By analyzing features such as striations chatter, marks, Roche-Moutonnet drumlins, and Esca networks, they can determine the direction, velocity, and reach of former glaciers. These landforms act as physical archives, recording the erosional and depositional forces that shaped the terrain during ice ages. High-resolution aerial photographs and satellite images have transformed the mapping and interpretation of these features across wide and often inaccessible regions. LiDAR surveys add another layer of detail by producing precise topographic models that reveal subtle landforms easily missed by other methods. When these visual datasets are combined with on-the-ground investigations, scientists can carry out thorough spatial analyses, distinguishing glacially formed features from those created by other geological processes. Equally important are geochronological approaches such as optically stimulated luminescence, radiocarbon dating, and cosmogenic nuclide dating, which allow researchers to establish when specific landforms developed. For instance, by measuring concentrations of cosmogenic isotopes like beryllium-10 and aluminum-26 in exposed rocks, scientists can estimate the time since a glacier retreated from a given location. These age constraints help assemble timelines of ice sheet advances and withdrawals, aligning physical evidence with climate records. Additional information comes from studying sediments left behind by glaciers, known as glacial till, along with the layered structure of related deposits. Sediment cores taken from glacial lakes or ocean basins preserve detailed records of past ice behavior, climate conditions, and sea level changes. Within these layers, pollen microfossils and chemical markers further assist in reconstructing environmental settings during different stages of the Ice Age. By combining landform analysis, dating techniques, and sediment studies, scientists build comprehensive reconstructions of former ice movements. These reconstructions not only clarify how ancient glaciers behaved, but also show how ice sheets reacted to climate changes, offering crucial insights into the complex processes that drive Ice Age cycles. Climate models are vital tools for untangling the complexity of Ice Age environments and their repeating patterns. These advanced simulations bring together numerous variables, including orbital factors, atmospheric composition, ocean circulation, and land surface characteristics to recreate the conditions of past glacial periods. By feeding data from geological evidence, ice cores, and sediment records into these models, researchers can produce dynamic representations of how temperature, precipitation, and ice sheet extent changed over thousands of years. At their foundation, these models are built upon the laws of physics and climate science, converting astronomical rhythms, such as those outlined by Milankovitch theory, into measurable effects within Earth's climate system. For instance, changes in Earth's axial tilt and orbital eccentricity alter both the distribution and strength of solar energy reaching the planet's surface, and climate models replicate these variations to examine the resulting climatic responses. These simulations also incorporate feedback processes, including shifts in surface reflectivity caused by growing ice sheets and changes in greenhouse gas levels, forming a comprehensive view of how climate evolves over time. The true power of climate models lies in their capacity to examine theories about past climate behavior. By running numerous scenarios under varying starting conditions, this method allows scientists to isolate the main forces behind glacial and interglacial cycles, and to understand how linked factors such as volcanic aerosols or the transfer of heat through ocean currents can intensify or weaken climate signals. In addition, models shed light on regional climate differences, showing why some areas experienced heavier glaciation while others remained comparatively stable, thereby supporting interpretations of local geological and paleontological records. Even so, the process remains deeply complex. The reliability of these models is strongly influenced by the quality and detail of the data that underpin them. Data that often carry unavoidable uncertainties. Furthermore, accurately representing the full breadth of Earth's climate system, particularly the interactions between oceans and the atmosphere, poses major computational challenges. Although climate models have grown steadily more advanced, they continue to be refined as scientists work to better represent the intricate feedback loops and long time scales that define Ice Age cycles. This continual improvement is gradually bringing researchers closer to understanding Earth's distant past and anticipating future climate behavior. Reconstructing environments from ancient ice ages is a demanding task, frequently complicated by the limited and fragile nature of the evidence available. One of the central difficulties arises from the incomplete or disrupted state of geological records. Over thousands of years, processes like erosion, sediment buildup, and tectonic movement can erase or deform vital clues, making it difficult to accurately reconstruct former climate conditions. For example, glacial deposits and landforms may be covered by more recent sediments or worn away entirely, leaving gaps in the environmental record. Another major challenge involves accurately dating materials linked to Ice Age settings. Although methods such as radiocarbon dating have transformed research in this field, they have clear limitations, particularly for samples that exceed their effective age range. As a result, age estimates can be broad, limiting the ability to reconstruct climate changes and ecological transitions in fine detail. Likewise, the preservation of organic remains, including plants or bones, varies greatly depending on local factors such as soil acidity, moisture levels, and temperature conditions that can either protect evidence or cause it to deteriorate rapidly. The diversity of Ice Age environments further complicates reconstruction efforts. Climate change did not unfold evenly across the planet. Differences in temperature, rainfall, and ocean circulation produced a wide range of habitats and climatic conditions. This unevenness forces researchers to combine evidence from many regions, each presenting its own preservation challenges. In addition, separating natural climate variation from human influence, particularly during the later phases of the Ice Age, adds further complexity to interpreting environmental records. Finally, dependence on indirect indicators such as isotopic signals preserved in ice cores or sediment layers introduces additional uncertainty. These proxies are often shaped by several interacting factors, making it difficult to convert them into precise environmental measurements. Together, these challenges require careful multidisciplinary strategies that draw on geology, chemistry, biology, and emerging technologies to expand our understanding of these ancient frozen landscapes, despite the inherent difficulty of reconstructing their detailed histories. Technological progress has dramatically reshaped our understanding of Ice Age processes, allowing scientists to explore Earth's frozen history with a level of detail never before possible. Remote sensing techniques, including satellite imagery and airborne LiDAR, have transformed the mapping and observation of vast ice sheets and glacial movement. These tools provide highly detailed, high-resolution views of ice sheet boundaries, flow dynamics, and surface characteristics, uncovering subtle changes occurring over decades and centuries that once went unnoticed. Such information is essential for understanding how ice masses expand, contract, and interact with their surrounding environment, helping to clarify the processes that controlled past ice ages. Alongside this, advances in radiometric dating techniques, including uranium series dating and optically stimulated luminescence, have greatly improved the precision of glacial chronologies and records of climate change. These methods provide more accurate age estimates for ice cores, sediments, and fossil materials, enabling researchers to link climatic transitions with geological and biological responses with greater certainty. Accurate dating has played a crucial role in reconstructing the timing and speed of ice sheet growth and retreat, as well as the ecological transformations that accompanied these changes. Ice core studies, supported by increasingly sophisticated drilling technologies, deliver remarkably detailed records of atmospheric composition, temperature trends, and greenhouse gas levels extending back hundreds of thousands of years. By retrieving deep ice cores from Greenland and Antarctica, scientists have revealed complex patterns in carbon dioxide, methane, and other greenhouse gases throughout glacial and interglacial cycles, directly connecting these variations to shifts in climate. Combining isotopic analysis with ice core data further enhances our understanding of temperature changes and their links to solar insolation and other external forcing factors. Computational modeling has also become a fundamental tool for exploring ice sheet dynamics and climate interactions. High-performance supercomputers make it possible to construct advanced climate models that integrate ocean circulation, atmospheric processes, and feedback mechanisms. Through these models, scientists can evaluate hypotheses about the drivers of glacial cycles, anticipate future climate developments, and interpret paleoclimate data within a unified framework. Collectively, these technological advances have transformed Ice Age research from largely descriptive geology into a robust, quantitative scientific discipline. They support detailed reconstructions of ancient environments, deepening insight into the forces that shaped Earth's frozen landscapes and guiding projections of future climate pathways. Gaining a full understanding of Ice Age complexity depends on a genuinely interdisciplinary approach that brings together knowledge from many scientific fields. Climatology offers the fundamental framework for understanding global temperature variations, orbital changes, and greenhouse gas levels that underpin the repeating pattern of glacial and interglacial phases. Paleoclimatology, through careful study of ice cores and sediment archives, reconstructs past climates in detail, documenting changes in atmospheric composition, temperature, and even volcanic activity that influenced environmental conditions. Geology and geomorphology add vital perspectives on how landscapes evolved, showing how glaciers carved valleys, reshaped mountains, and deposited sediments over thousands of years. These physical records not only reflect ice sheet behavior, but also affect modern sea levels and coastal forms. Glaciology, in turn, concentrates on the physical behavior of ice sheets, examining their movement, accumulation, and melting, to explain how ice masses advance and retreat. Biological sciences, especially. Paleoecology and evolutionary biology reveal how plants and animals responded to major climatic shifts. By analyzing fossil evidence, pollen records, and sedimentary DNA to rebuild ancient ecosystems and track migration patterns. Archaeology complements these insights by uncovering how humans interacted with Ice Age environments, shedding light on strategies for adaptation and survival. Technological progress has encouraged collaboration across disciplines, particularly through remote sensing and computer modeling, which increasingly simulate climate systems and ice sheet behavior with high accuracy. These models combine geological, climatic, and biological information, allowing researchers to test ideas about past environmental change and its effects on ecosystems. As scientific investigation continues to advance, integrating these diverse perspectives becomes ever more important. Each field contributes a crucial element together, forming a comprehensive understanding of the Ice Age's complex dynamics. This collaborative approach not only enriches knowledge of past climate variability, but also supports forecasts of future climate change and its potential consequences for modern ecosystems. The merging of geology, climatology, biology, archaeology, and technology highlights the truly interdisciplinary effort required to unravel the deep mysteries of the Ice Age. The recovery and study of ancient DNA have further transformed our understanding of Ice Age ecosystems, providing a molecular glimpse into the past that enhances and extends traditional fossil and sediment-based evidence. In contrast to morphological remains, which often offer only limited information about relationships between species or shifts in population structure, ancient DNA gives scientists the ability to follow genetic lineages, migration routes, and strategies of adaptation with striking accuracy. This molecular perspective has revealed species that were previously unknown, exposing a far more complex picture of biodiversity that existed during glacial times. By sequencing genomes taken from exceptionally preserved material, including bones locked in permafrost or tissues frozen by extreme cold, grounded researchers are able to rebuild entire population histories, uncover episodes of interbreeding between different species, and identify genetic traits linked to survival in cold environments. Research on woolly mammoths and ancient horses, for instance, shows how their populations expanded, contracted, and at times hybridized as climates shifted. Such genetic evidence explains how species endured environmental change, often through movement into refugia, or by developing highly specialized characteristics, and in doing so reveals both the strength and fragility of Ice Age communities. Ancient DNA further sharpens our understanding of predator-prey relationships, illustrating how populations rose and fell together, and how ecological balances transformed across thousands of years. It also assists in pinpointing the timing and drivers of extinctions, highlighting the intricate interaction between climatic shifts and human influence. Beyond the past, this molecular information contributes to models that explore how modern species may react to current environmental pressures by examining the genetic flexibility for adaptation demonstrated by Ice Age survivors. Overall, the study of ancient DNA has reshaped the story of Ice Age ecosystems, moving it from a narrative built mainly on physical traces to a living account constructed from genetic evidence. It enables scientists to look deeply into the evolutionary processes that shaped life in frozen environments, emphasizing both the richness of past biodiversity and the biological mechanisms that allowed survival amid constant climatic upheaval. As research advances, ancient DNA continues to strengthen our understanding of the deep connections between ancient ecosystems and present-day biodiversity, laying the groundwork for a more detailed view of how ecosystems respond to change. The remains of Ice Age glaciers still influence Earth's landscapes and ecosystems long after the ice itself has vanished. These immense bodies of ice carved valleys, fjords, and basins, creating landforms that continue to shape regional climates and habitats today. The enormous weight of glaciers at their greatest extent pressed down on the land, and when the ice retreated, the surface slowly rose in a process known as isostatic rebound, forming elevated terrain and redirecting drainage systems. Such transformations have determined the distribution of freshwater productive soils and natural barriers directly affecting modern ecosystems and patterns of human settlement. Glacial features left behind, including moraines, drumlins, and outwash plains, now function as important ecological environments. These formations often support distinctive plant and animal communities that have adapted to their specific conditions. In many cases, nutrient-rich sediments deposited by glaciers encourage diverse plant growth, which then sustains a wide range of animal life. In certain regions, these deposits form the basis of agriculture by providing fertile ground, showing how ancient glacial activity continues to support human livelihoods. The influence of glacial remnants also reaches beneath the surface into hydrological systems. Meltwater from lingering ice feeds rivers and lakes, preserving ecological connections and supporting biodiversity. Where glaciers once dominated ongoing meltwater shapes, freshwater habitats influences migration routes for aquatic species and affects water availability for nearby populations. The physical changes created by glaciers also play a role in climate regulation. Large ice sheets and the release of their meltwater affect ocean currents and atmospheric circulation, with consequences for both regional and global climate patterns. These interactions demonstrate that the legacy of Ice Age glaciers remains embedded within the climate systems that govern present and future environmental conditions. Gaining an understanding of these glacial remnants provides valuable insight into the resilience and adaptability of ecosystems. By recognizing how landscapes have been reshaped by ice over time, we can better appreciate their continuing importance and apply this knowledge to managing environmental change. Reflecting on the lasting impact of ancient glaciers offers a broader perspective on Earth's constantly evolving systems lessons that are especially relevant in the face of modern climate challenges. Past ice ages stand as powerful reminders of the dynamic nature of Earth's climate and its ability to undergo profound transformation. By studying these frozen eras, we uncover important insights into the processes that govern climate variability and the ability of life to endure under extreme conditions. One central lesson lies in understanding the delicate equilibrium between greenhouse gases and global temperatures. Throughout ice ages, changes in atmospheric CO2 and methane concentrations played decisive roles in triggering the onset and the end of glacial periods. Today, recognizing these feedback mechanisms highlights the critical need to closely monitor greenhouse gas emissions, as even minor variations can set off major climatic shifts. The historical patterns of ice sheet growth and retreat also demonstrate the powerful influence of ocean currents and continental arrangements on climate regulation. During glacial phases, shifts in ocean circulation altered how heat was distributed around the planet, shaping regional climates and sea levels. This understanding reinforces the importance of protecting healthy ocean systems and addressing human-induced disturbances such as pollution and overfishing, which threaten the stability of today's climate. Another key lesson concerns the resilience and adaptability of ecosystems and species. Records of extinctions and migrations during ice ages show how life responds to rapid environmental change, sometimes through remarkable innovation and at other times through vulnerability. Examining these responses helps guide modern conservation efforts. emphasizing the importance of maintaining genetic diversity and enabling species to move as they confront ongoing climate change. In addition, archaeological evidence of human adaptation during ice ages, seen in technological advances, migration patterns, and social organization, illustrates humanity's capacity for creativity and resilience in the face of hardship. These examples encourage modern societies to pursue sustainable practices and adaptive policies that strengthen resilience against future climatic disruptions. Ultimately, exploring past glacial cycles reveals the deep interconnectedness between Earth's climate systems and biological responses. Recognizing these lessons promotes a proactive approach to contemporary climate challenges, underlining the value of scientific awareness, adaptive management, and global cooperation to reduce the impacts of present and future environmental change. Modern permafrost and frozen ground remain as lasting traces of ancient Ice Age conditions, offering a direct connection to Earth's glacial past. During the last Ice Age, massive ice sheets spread across large areas of the Northern Hemisphere, pressing down on the land with enormous weight and dramatically altering surface temperatures and water systems. As these vast glaciers advanced and retreated over thousands of years, they reshaped the terrain, carving valleys, fjords, and other landforms that are still visible today. The extensive areas of permanently frozen ground that endured through these times are known as permafrost soil rock and organic material that stays at or below freezing temperatures year-round. The formation of permafrost is closely linked to Ice Age climates when persistent cold prevented widespread thawing. At glacial maxima, freezing conditions pushed permafrost far into continental interiors, preserving ancient organic matter such as plant and animal remains. This frozen material provides valuable evidence of past ecosystems' climate changes and even the movement patterns of Ice Age animals. As temperatures rose and glaciers retreated at the close of the last Ice Age, some permafrost regions began to thaw, releasing stored greenhouse gases like methane and carbon dioxide, which contributed to later climate variability. Today's permafrost regions therefore function as living records of Ice Age environments. Their extent and stability reflect the balance between present-day climate conditions and the lingering influence of past glacial periods. The thawing of permafrost carries significant consequences for global climate change, as the release of trapped greenhouse gases can intensify warming trends. At the same time, in certain high-latitude regions, permafrost persists because of continued cold conditions, echoing the harsh climate of the Ice Age. These frozen landscapes continue to shape ecosystems, affect infrastructure development, and act as vital indicators of how Earth's climate system responds to ongoing environmental change, linking the present directly to the frozen epochs of the distant past. Ice Age cycles represent fundamental forces behind long-term climate variability, shaping Earth's environmental patterns over tens to hundreds of thousands of years. These cycles are largely controlled by subtle changes in Earth's orbital characteristics, specifically eccentricity, axial tilt, and precession, which modify the distribution and strength of solar radiation reaching the planet's surface. As a consequence, these processes generate extended phases of cooling and warming that reach far beyond individual glacial and interglacial stages. When eccentricity and axial tilt increase, polar regions receive reduced solar energy during the winter months, creating conditions that encourage the growth and spread of ice sheets and glaciers. In contrast, when orbital arrangements allow sunlight to strike the planet more directly, ice masses withdraw, ushering in warmer interglacial periods. These repeating shifts affect not only the size and thickness of ice formations, but also shape wider climate systems, including atmospheric circulation patterns of precipitation and the movement of ocean currents. Such changes can modify the global distribution of heat, influencing climate stability across thousands of years. The combined influence of these cycles appears as a pattern of long-term climate oscillations that regulate the timing, length and strength of glacial episodes. This steady rhythm of climatic change has historically governed the rise and decline of ecosystems, driving species to migrate, adapt or disappear, and shaping the evolutionary paths of plants and animals alike. Variations in sea level linked to glacial cycles, sometimes reaching hundreds of meters, have periodically exposed or submerged continental shelves, opening or closing migration routes and altering ocean pathways that are essential to climate regulation. This complex interaction between orbital dynamics and climate feedback mechanisms highlights how Ice Age cycles function as a natural thermostat, guiding Earth's long-term climate variability. Gaining insight into these cycles reveals the intricate relationship between celestial mechanics and terrestrial climate systems, showing the profound influence of cosmic rhythms on the planet's environmental history. This understanding, in turn, provides critical context for evaluating present-day climate change and its possible long-term consequences. The lasting imprint of Ice Age formations continues to play a major role in shaping modern patterns of human settlement and infrastructure development. Landscapes once molded by glaciers, including deep valleys, nutrient-rich moraines, and broad plains, present both benefits and difficulties for contemporary communities. Glacially carved valleys, for example, often become natural routes for transportation networks and urban growth, easing movement across otherwise challenging terrain. At the same time, fertile soils deposited by glaciers frequently support agriculture, enabling high population densities in certain regions. Yet these same features can also introduce risks. Old glacial sediments may weaken structural foundations or raise the likelihood of flooding during periods of heavy rainfall or rapid melt. Permafrost, a defining characteristic of many Ice Age terrains, has a significant impact on infrastructure planning. Its presence requires specialized engineering approaches to prevent ground subsidence and structural failure, particularly as warming temperatures threaten its long-term stability. As permafrost thaws, ground that was once solid can collapse, damaging roads, pipelines and buildings, thereby complicating development efforts. This process highlights the delicate balance between using landscapes shaped by ancient ice and addressing the vulnerabilities they present. In addition, the distribution of remaining glacial features affects water management. Moraines and outwash plains often function as natural aquifers, providing freshwater supplies, yet their uneven terrain can make drainage and flood control more difficult. Coastal regions influenced by glacial retreat are likewise affected by changing sea levels, shaping urban planning decisions, and the durability of coastal infrastructure. The influence of past glaciations also extends into hazard assessment and land use planning. Identifying areas at risk from glacial lake outburst floods or landslides linked to glacial deposits informs strategies for reducing danger. As societies increasingly respond to climate variability, understanding the role of Ice Age landscapes becomes ever more important. This knowledge allows planners to make informed decisions about land use, create resilient infrastructure, and protect natural features that continue to shape human life. Within these landscapes, transformed long ago, the accelerating pace of global warming raises serious concerns about the preservation and future stability of features left behind by the Ice Age. Many of these elements, including ancient ice sheets, layers of permafrost, and glacial landforms, act as crucial records of Earth's climatic history, offering valuable insight into natural climate variation. As temperatures continue to rise, the fragile equilibrium that sustains these features may be disturbed, potentially leading to irreversible changes. For instance, the loss of remaining ice sheets could erase landforms that have endured for thousands of years, removing important geological evidence of past glacial periods. This loss would reduce scientists' capacity to reconstruct detailed records of past climates records that are vital for understanding long-term climate behavior. Permafrost regions, which often preserve organic material dating back to previous ice ages, are especially at risk. When permafrost thaws, it can release enormous amounts of stored greenhouse gases, including methane and carbon dioxide, thereby intensifying present-day warming trends. These feedback processes not only speed up climate change, but also threaten to disturb the climate signals locked within these frozen layers, making future climate modeling more complex and uncertain. In addition, the destabilization of permafrost can cause ground subsidence, altering landscapes and ecosystems that have remained largely unchanged since the Ice Age, and disrupting both natural habitats and human communities. The possible loss of glacial features also affects projections of sea level rise. As remaining glaciers continue to melt, their contribution to rising sea levels becomes harder to predict, particularly if feedback mechanisms accelerate the rate of ice loss. Such developments could resemble or even exceed the impact seen at the close of earlier glaciations, but unfolding at an unprecedented pace. As a result, the degradation of Ice Age legacy features under modern warming conditions complicates the interpretation of paleo-environmental evidence, making it more difficult to separate natural climate variability from human-induced change. Understanding how these features respond to warming is essential not only to protect Earth's geological heritage, but also to improve models that forecast future climate pathways. Safeguarding these archives enables scientists to better anticipate how ongoing climate changes may reshape the planet in the centuries ahead, highlighting the importance of integrating lessons from past climate responses into contemporary predictive systems. The study of ice ages offers invaluable knowledge that strengthens the precision and reliability of climate prediction models. By analyzing geological remnants left behind by glacial periods such as sediment layers, ice cores, and landforms, scientists can assemble detailed records of historical climate variability. These natural archives preserve information about atmospheric composition, temperature changes, and oceanic conditions across tens of thousands of years. Ice cores in particular function as chronological records, trapping gases like carbon dioxide and methane, which allows researchers to reconstruct ancient greenhouse gas levels with remarkable accuracy. This long-term perspective shows how Earth's climate system responded to different forcing factors, including orbital variations and volcanic events, helping scientists recognize patterns and thresholds that led to transitions between glacial and interglacial states. Moreover, studying the behavior of ice sheets during past ice ages informs climate models about feedback mechanisms and non-linear responses within the system. For example, understanding how the expansion and retreat of ice sheets affected sea levels and surface reflectivity improves predictions of future sea level rise under various greenhouse gas emission scenarios. Investigations of erosion and deposition patterns created by glaciers also help calibrate models of surface processes and sediment movement, which are essential for simulating interactions between climate and the land surface. Integrating evidence from Ice Age deposits enhances model resolution by grounding simulations in real-world examples of climate change spanning millennia. This historical framework refines model sensitivity to different forcing influences, resulting in more robust projections. It also deepens understanding of the potential timing and scale of climate shifts, which is critical for preparing for future variability. As climate models continue to advance, they become better suited to predicting the complex interactions among atmospheric, oceanic, and terrestrial systems. Therefore, the study of ice ages not only sheds light on Earth's climatic past, but also provides a vital foundation for anticipating and managing future climate challenges. Ice Age deposits act as invaluable archives of Earth's geological and environmental history, and play an important role in the exploration and management of natural resources. These deposits, made up of sediments, till, and other materials, left behind by glaciers and ice sheets, hold extensive information about ancient climates, vegetation patterns, and mineral distributions. Examining them enables geologists and resource managers to identify regions rich in minerals, including ores, coal, and hydrocarbons, which often form in landscapes shaped by glacial activity. For example, the erosion and deposition processes driven by moving ice frequently concentrate valuable minerals in particular areas, making such regions especially attractive targets for resource exploration. Beyond mineral resources, Ice Age deposits play a crucial role in identifying aquifers and underground water reserves. Sediments laid down by glacial meltwater streams and till layers often create porous permeable formations capable of holding large volumes of fresh water. A clear understanding of the stratigraphy of these deposits allows scientists and planners to define aquifer limits and evaluate the long-term viability of groundwater use, particularly in areas where modern water supplies rely heavily on ancient glacial formations. In addition, Ice Age deposits strongly influence land use planning and environmental management. Regions blanketed by glacial till and related sediments can affect soil quality, fertility, and ground stability, with direct consequences for farming and construction. Identifying the distribution and makeup of these deposits supports sustainable land management, helping to prevent problems such as soil erosion or ground subsidence. In coastal areas, traces of glacial sediments also contribute to assessments of sea level change, aiding predictions of future shoreline movement and supporting strategies to mitigate the impacts of rising seas. Research into Ice Age deposits further contributes to environmental conservation. By studying the climatic information preserved within these sediments, scientists gain insight into how past ecosystems responded to shifts in climate knowledge that helps guide efforts to protect biodiversity in the face of ongoing climate change. Taken together, these deposits are far more than leftovers from a frozen era. They act as living records that deepen our understanding of Earth's natural resources and environmental resilience, supporting responsible exploration and sustainable management in an evolving world. This close connection between geology and resource stewardship highlights the significance of Ice Age deposits linking ancient processes with present-day demands. As researchers continue to examine these deep layers, they uncover knowledge essential for meeting future challenges and opportunities. The unearthing of extraordinary fossils and artifacts from the Ice Age has greatly expanded our knowledge of the life that existed during this cold period. Among the most important discoveries are the remains of large megafauna, such as mammoths, mastodons, and saber-toothed cats. These fossils reveal not only the physical traits and adaptations of these animals, but also clarify their ecological roles within Ice Age environments. For example, exceptionally preserved mammoth remains found in the permafrost of Siberia have offered detailed information about their diet, migration routes, and even signs of illness or injury, creating a vivid picture of their struggle to survive in extreme conditions. Equally significant is the discovery of the Lascaux cave paintings in France, which provide valuable insight into the cultural lives of Ice Age humans. These detailed images of animals like aurochs and horses reflect the central role of hunting and spiritual symbolism in early societies. Such finds highlight the deep connection between humans and their surroundings, revealing not only practical survival methods, but also the emergence of artistic expression and ritual behavior. The discovery of the Philendorf Venus figurine adds further evidence of symbolic thinking and social organization among early humans, sculpted from limestone and featuring carefully rendered details. These figures suggest that Ice Age communities practiced rituals linked to fertility survival or spiritual beliefs, offering a window into their understanding of the world. In more recent decades, excavations at cave sites such as Altamira and Chauvet have revealed extraordinary wall paintings, some more than 30,000 years old. These artworks portray animals alongside abstract symbols, demonstrating the growing cognitive and cultural sophistication of Ice Age humans. Each new discovery not only broadens our knowledge of the plants and animals of the time, but also highlights the remarkable creativity and adaptability of humans living under harsh conditions. Together, these fossils and artifacts act as essential clues for uncovering the story of life during the Ice Age, connecting us with a distant world marked by resilience and endurance. One of the most important archaeological locations shedding light on Ice Age life is the La Brea tar pits in Los Angeles. Unlike conventional fossil sites formed through layered sediment, these tar pits functioned as natural traps, preserving an extraordinary snapshot of Pleistocene megafauna and smaller animals, and offering invaluable insight into the biodiversity, ecology, and survival strategies of the era. Over thousands of years, sticky asphalt rose to the surface, trapping animals that strayed too close and were unable to escape. This process produced a remarkable collection of well-preserved bones, many retaining impressions of soft tissue, which have since been carefully excavated and analyzed. The findings from La Brea have expanded our understanding of Ice Age animals far beyond simple skeletal remains. The wide range of species, from mammoths and mastodons to dire wolves, saber-toothed cats, and giant ground sloths, creates a vivid portrait of the intricate predator-prey relationships that once shaped Ice Age ecosystems. By studying these remains, scientists have been able to reconstruct food webs, migration routes, and patterns of territorial behavior, revealing how these animals adjusted to shifting climates and changing access to resources. The presence of juvenile and injured individuals among the finds has also offered important clues about survival pressures and the impact of environmental stress. In addition, the surrounding context of these discoveries has helped clarify the timing and speed of Ice Age extinctions. Many of the species recovered from the tar pits vanished soon after the last glacial maximum, pointing to climate change and human activity as major contributing factors. The discovery of tools and signs of human interaction within the same geological layers has further enriched our understanding of early human hunting methods and adaptive strategies in a world undergoing rapid transformation. The importance of the La Brea tar pits reaches far beyond simple paleontological interest. They provide a unique window into the fragile balance of Ice Age ecosystems and the forces that led to the rise and collapse of megafaunal communities. These findings continue to shape scientific models of climate change, extinction processes, and human-environment relationships, demonstrating how natural traps can preserve an extraordinary archive of information for future generations. Their value lies not only in what they reveal about ancient life, but also in how they help us interpret ecological changes still unfolding today. The discovery of woolly mammoth remains represents a crucial milestone in understanding Ice Age life, offering rare and invaluable insights into the environment, ecology, and human interactions of this frozen era. These exceptionally preserved fossils, often uncovered in permafrost regions, provide an unusually detailed glimpse into a species that once dominated icy grasslands. In some cases, preservation includes soft tissues, hair, and even stomach contents, allowing researchers to reconstruct not only the physical appearance of these animals, but also elements of their diet, health, and behavior. Such evidence deepens our understanding of the ecological networks that supported Ice Age megafauna and the climatic conditions that shaped their lives. Beyond rebuilding past ecosystems, woolly mammoth remains also offer direct proof of adaptive strategies. Their dense fur, thick fat layers, and specialized limb structures illustrate how they evolved to survive extreme cold, shedding light on the evolutionary pressures faced by large animals in glaciated environments. These discoveries help clarify broader patterns of adaptation and extinction, particularly as many mammoth populations disappeared toward the end of the Ice Age, a process closely linked to both climate shifts and human hunting. The importance of these finds extends further into the story of early human life. Many locations containing mammoth remains also yield tools, weapons, or carvings associated with human activity, suggesting that these animals played a central role in Ice Age survival. As a result, the remains act as a gateway to understanding how humans hunted, scavenged, and made use of mammoth resources, shaping their cultural traditions. These interactions highlight the creativity and resourcefulness of Ice Age humans, as they adapted to harsh environments and made use of available materials. In essence, woolly mammoth remains are far more than simple fossils. They function as time capsules, revealing the complex interplay between climate ecology and human ingenuity during the Ice Age. Ongoing research continues to refine our picture of a world shaped by relentless climatic change, making each new discovery a vital piece of our ancient story. Cave paintings and carvings stand as extraordinary windows into the minds and lives of Ice Age humans, offering insights that reach far beyond basic survival. These ancient artworks reveal layers of cultural expression, spiritual belief, social structure, and interaction with the natural world. Unlike many other archaeological objects, images painted or engraved on cave walls preserve vivid narratives of human experience, frequently portraying animals' hunting scenes and symbolic forms. Detailed representations of megafauna such as mammoths, bison, and reindeer underscore the central role these animals played in daily life, not only as sources of food and materials, but also as powerful symbols filled with spiritual meaning. The deliberate choice of subjects reflects a deep awareness and respect for the environment, showing that Ice Age humans were careful observers of the world around them. Such artworks likely served ritual or teaching purposes, possibly guiding hunting practices or strengthening social ties within groups. Analysis of artistic style and placement within caves also reveals important aspects of cognition and communication. The use of perspective symbolism and sequential imagery points to advanced mental abilities, including abstract thinking and shared cultural rules. In some cases, recurring patterns and motifs may represent early efforts to record stories or preserve collective memory, creating cultural continuity across generations. Moreover, certain cave sites display signs of ritual behavior, such as the use of red ochre and intentionally arranged carvings, suggesting that these spaces held ceremonial or spiritual significance. The blending of art with the natural setting reflects a worldview in which humans saw themselves as deeply connected to the animals and spiritual forces depicted in their creations. Together, these artistic expressions form a cultural record that complements physical remains, like tools and shelters, enriching our understanding of Ice Age human life. They assist in rebuilding an understanding of social organization systems of belief and relationships with the environment during the Ice Age, forming a deeper and more detailed picture of human adaptability and creativity in a demanding climate. By studying these ancient images, we gain valuable insight into how early humans viewed and engaged with their surroundings, establishing a foundation for interpreting later cultural and technological progress. Major archaeological sites have acted as essential gateways to understanding Ice Age environments, providing concrete glimpses into a long-lost frozen world. These sites, often preserved within ice caves or layered sediments, have yielded an abundance of evidence through the discovery of tools, bones, shelters, and artworks that reveal how early humans and animals interacted with their environment. Their strategic locations, including caves in Europe, shelters in Siberia, and campsites near ancient lakes, have preserved material with remarkable clarity, enabling researchers to reconstruct climate conditions, vegetation patterns, and animal populations, characteristic of different Ice Age phases. The importance of these sites goes far beyond the objects found within them. They function as chronological reference points, offering precise dating through radiocarbon and other scientific methods. This temporal framework helps establish the sequence of environmental changes alongside human responses. For example, the finding of mammoth remains together with advanced tools demonstrates not only the presence of large megafauna, but also the technological skill of Ice Age humans in making use of available resources. In the same way, cave paintings and carvings portray animals and landscapes, providing visual evidence of plant and animal life that no longer exists, thereby enriching our knowledge of paleoecology. Sites such as the Denisova Cave in Siberia have revealed ancient human genetic material, uncovering migration routes and interbreeding events that played a role in shaping human evolution. These discoveries challenge earlier assumptions and highlight the significance of archaeological sites as repositories of both biological and environmental information. In addition, sediment layers and pollen studies from these locations offer insight into climatic variations, helping scientists reconstruct temperature ranges, rainfall patterns, and vegetation zones during different Ice Age intervals. As research methods become increasingly advanced, the role of archaeological sites in Ice Age studies continues to grow. They operate as natural laboratories where multiple disciplines, including archaeology, paleontology, geology, and genetics, come together. These places are not only windows into the distant past, but also keys to understanding how climate change, ecological transformation, and human ingenuity combine to shape the legacy of the Ice Age landscape. Continued excavation and analysis promise to deepen our understanding of this intricate chapter in Earth's history. Recent technological innovations have dramatically reshaped Ice Age research, opening new paths to understanding this complex period. Developments such as high-resolution radiocarbon dating, LiDAR scanning, and genomic sequencing have allowed scientists to refine timelines and uncover details once hidden beneath layers of sediment or ice. These techniques have greatly increased the accuracy of dating artifacts, fossils, and sediment deposits, enabling researchers to identify migration patterns and climate shifts with an unprecedented level of precision. For instance, The analysis of ancient DNA from both humans and megafauna has revealed complex relationships between species, shedding light on migration routes and adaptive strategies that supported survival during changing glacial conditions. LiDAR technology, originally created for topographic mapping and military use, has become a vital tool for identifying subtle landscape features concealed beneath vegetation or ice. By producing detailed three-dimensional maps of Paleolithic sites, researchers can locate previously unrecognized habitation areas, tool concentrations, and migration pathways. This has led to the identification of early human settlements in regions once considered uninhabitable, expanding our understanding of human resilience and adaptability. In a similar way, remote sensing satellites equipped with multispectral imaging enable large-scale surveys of sediments and landforms, helping trace the advance and retreat of glaciers over thousands of years. Advances in computational modeling have also transformed the study of ice sheet behavior. By combining climate records, ocean circulation data, and geological evidence, within complex simulations, scientists can recreate past climate scenarios and explore how ice sheets responded to different driving forces. These models help resolve debates about the timing and causes of rapid glacial advances or retreats, further deepening our understanding of ice sheet stability and ice age dynamics. Genomic technologies have become essential in uncovering the genetic diversity and migration routes of both ice age species and human populations. By sequencing ancient DNA extracted from well-preserved remains, scientists gain valuable insights into adaptation processes, population bottlenecks, and interactions between different species. These advances have reshaped established timelines of human movement and extinction events, revealing a dynamic relationship between shifting climates and biological responses. The continued integration of these technologies challenges long-standing assumptions and encourages the development of new hypotheses. As analytical tools advance further, they hold the promise of deepening our understanding of Ice Age complexity, revealing a richer and more detailed account of Earth's frozen past. The effort to comprehend the Ice Age through its many discoveries has also given rise to ongoing debates and controversies. At the heart of these discussions lies the interpretation of archaeological and geological evidence, which often presents complex and sometimes contradictory stories about the timing scale and consequences of glacial periods. A major point of disagreement concerns the exact chronology of glacial advances and retreats. Although radiocarbon dating and ice core studies have established crucial timelines, inconsistencies between dating techniques and gaps in the fossil record lead some researchers to question whether global ice sheet changes were truly synchronized. These debates shape how scientists interpret the speed of climate change and its regional differences, influencing broader reconstructions of Earth's climatic history. Another persistent controversy focuses on the causes of sudden climate shifts observed during the late Pleistocene. Some researchers contend that rapid transitions such as the Younger Dryas were mainly triggered by large influxes of fresh water that disrupted ocean circulation, while others argue for heightened sensitivity to orbital changes or the influence of volcanic activity. This debate centers on how proxy data from sediments and ice cores are interpreted, with each perspective highlighting different mechanisms capable of driving such abrupt transformations. These disagreements are not purely theoretical. They directly affect how we assess the stability of modern climate systems and the risk of sudden changes. In addition, interpretations of fossil evidence related to megafaunal extinctions remain highly contested. While climate change clearly played a role, many scientists continue to debate how much human actions, including hunting pressure and habitat modification, contributed to these losses. The varying timelines of human arrival across regions further complicate this issue, prompting discussion over causation versus coincidence. This highlights the necessity of combining multiple lines of evidence to develop a more refined understanding of the interaction between natural climate variability and human influence. Such debates illustrate the evolving nature of paleoclimatology and emphasize the value of ongoing research. They compel scientists to improve methods and revisit established ideas, ultimately expanding our knowledge of Earth's climatic past. These discussions also remind us that even well-supported conclusions remain open to revision as new evidence comes to light, underscoring the continually unfolding story of our planet's frozen ages. These transformative discoveries act as crucial tools for unlocking the complex history of Earth's past climates, offering insights that go far beyond a simple timeline of ice sheet expansion and retreat. Through precise dating of ancient sediments, ice cores and fossil remains, researchers can reconstruct detailed climate fluctuations spanning hundreds of thousands of years. This information reveals patterns in temperature change, atmospheric composition, and ocean dynamics, allowing scientists to identify links between orbital cycles, greenhouse gas levels, and shifts in climate. The exceptional preservation of ancient plants and animals within ice and sediment layers provides direct evidence of how ecosystems responded to changing temperatures and environmental pressures. For instance, changes in species distribution and the timing of migrations or extinctions help define the limits of climate tolerance and illustrate the speed of ecological adaptation. These insights improve models that explain how climate variability affects biological resilience and vulnerability, offering perspectives that are highly relevant to understanding present-day climate change. Moreover, the examination of glacial deposits and landforms has clarified both the reach and the speed of ice sheet movement, sharpening our understanding of ice behavior under varying climatic conditions. This progress has in turn improved reconstructions of past sea levels, demonstrating the far-reaching influence of ice age cycles on continental coastlines and global geography. Such reconstructions have become essential for placing modern sea level rise and coastal vulnerability into a broader historical context. Alongside this, interdisciplinary methods that combine climate modeling, geology, paleobotany, and archaeology have greatly expanded our understanding of how climate change has shaped human evolution, migration pathways, and cultural development. These findings highlight the deep interconnectedness of climatic and biological systems across geological timescales. As research continues to advance, scientists are steadily uncovering additional layers of complexity within Earth's climatic history. These insights not only enrich our understanding of past climate variability, but also strengthen predictive models that are crucial for confronting present and future climate challenges. This evolving perspective reinforces the importance of integrating paleoclimatic evidence into wider Earth system science, ultimately helping to inform strategies that support resilience in a warming world. The quest to understand Ice Age phenomena unfolds across a shifting landscape of scientific frontiers and significant challenges. As researchers probe deeper into Earth's glacial past, they face the difficulty of untangling intertwined climate signals preserved within geological archives. One major frontier involves refining chronological frameworks, dating ancient ice cores, sediments, and fossils with ever greater accuracy. Innovations in isotopic analysis and high-resolution stratigraphy have opened promising pathways, yet uncertainties persist when attempting to correlate records across different regions and timescales. This complexity complicates efforts to reconstruct the exact timing and speed of climatic transitions, including the onset and conclusion of glacial periods. Another central challenge lies in interpreting the vast and often incomplete records of past climate. While ice cores from Greenland and Antarctica provide invaluable information on atmospheric composition and temperature change, they capture only a limited portion of the global system. Broadening this perspective requires the integration of diverse proxies, including marine sediments, terrestrial deposits, and cave records, each carrying its own challenges related to interpretation and dating. Bringing these varied sources together demands advanced models capable of merging disparate data sets into coherent climate reconstructions. The complex behavior of ice sheets themselves presents further obstacles. Contemporary climate models aim to simulate ice sheet responses to warming conditions, yet accurately representing processes such as basal sliding calving and subglacial hydrology remains challenging. These underlying mechanisms strongly affect ice sheet stability and carry direct consequences for projections of future sea level rise. Adding feedback processes, including albedo effects and interactions between ice and climate, introduces additional layers of difficulty into modeling efforts. The challenge also extends to understanding how Ice Age cycles interacted with Earth's biosphere and with human societies. Addressing this question requires not only paleoclimate records, but also contributions from archaeology, genetics, and ecology disciplines that must come together to reveal how ancient populations responded to climatic variability. Connecting these fields and translating insights from the past into meaningful future projections represents one of the most ambitious frontiers in climate science today. As technology continues to advance, so too does our ability to confront these challenges, offering the promise of a deeper and more comprehensive understanding of Earth's frozen epochs. Developments in artificial intelligence AI and machine learning ML are set to transform our understanding of Ice Age cycles. By enabling powerful analysis of complex climate data, these technologies are particularly effective at identifying subtle patterns within enormous data sets. Patterns that often escape traditional statistical approaches. Through the integration of proxy records such as ice cores, sediment layers, and fossil distributions, AI-based methods can reconstruct highly detailed timelines of climate variation with improved accuracy. For instance, ML models are capable of detecting recurring cycles or key triggers related to orbital changes, greenhouse gas levels, and ocean dynamics, revealing the intricate interactions that drive glacial advances and retreats. In addition, simulations powered by AI can account for multiple variables at once, allowing researchers to explore different hypotheses about ice age behavior under varying boundary conditions. These models can examine how small changes in Earth's orbit or atmospheric composition may influence long-term climate trends, offering insight into the thresholds that govern transitions between glacial and interglacial phases. As fresh information from ongoing drilling initiatives, satellite monitoring, and a wide range of climate proxies is brought together, machine learning systems continually sharpen their forecasts, improving both accuracy and depth of insight. One particularly promising use involves neural networks, examining ancient biological and geological archives, uncovering evidence of how ecosystems and landscapes reacted to past climate shifts. This approach helps clarify feedback processes that either intensified or moderated climatic changes, thereby informing models of future climate stability. AI tools also make it possible to detect regional differences in ice sheet behavior, showing how local conditions contributed to broader global patterns. By applying AI and ML methods, researchers can further enhance the precision of dating major events in Ice Age history, including rapid ice loss phases or abrupt climate reversals. These refined timelines are essential for linking climate events to possible external drivers such as volcanic eruptions or variations in solar activity. Together, these technological developments significantly expand our understanding of past climate variability, equipping us with crucial knowledge to better anticipate future climate pathways in an increasingly warming world. Investigating past ice ages provides invaluable insight into the sensitivities and feedback mechanisms within Earth's climate system, which are fundamental for improving future climate projections. By analyzing the timing, duration, and speed of glacial and interglacial transitions, scientists can identify thresholds and tipping points that may signal sudden climate changes ahead. Historical records demonstrate how interconnected elements, including ice sheet mass balance, atmospheric greenhouse gas levels, and ocean circulation responded to evolving conditions. This understanding allows climate models to incorporate more realistic interactions and non-linear responses. Ice core and sediment data have been central to reconstructing ancient atmospheric compositions, offering reference points against which model simulations can be tested. For example, examining how greenhouse gas concentrations rose and fell alongside temperature during earlier climate cycles helps refine estimates of climate sensitivity to trace gas changes. Detailed records of ice sheet expansion and retreat also guide predictions about how modern ice masses may respond to current warming, including the possibility of non-linear collapse events and their consequences for sea level rise. In addition, paleoecological evidence, such as changes in plant life, animal populations, and human distribution, emphasizes the role of ecological resilience and adaptation. These insights help models more accurately represent feedbacks between climate and the biosphere, including carbon cycle processes. Recognizing the speed of past climate shifts, especially during abrupt episodes like Dansgaard-Oeschger oscillations, highlights the potential for rapid transformations that challenge simple linear forecasts. This awareness drives the development of models capable of capturing sudden, large-scale changes in climate states. By combining detailed historical reconstructions with growing computational capabilities and expanding observational datasets, climate scientists continue to refine models that better represent the complex dynamic interactions within Earth's climate system. Such advancements are essential for producing more accurate and dependable projections of future climate change, ultimately supporting societies in preparing for and reducing risks rooted in Earth's deep climatic past. Improving climate models to enhance predictions of long-term Earth system change depends on integrating increasingly advanced data sources and a deeper understanding of complex feedback processes. Progress in paleoclimate reconstruction drawn from ice cores, sediment layers, and other proxies provides critical benchmarks that allow models to be calibrated against known past climate variations, including the dramatic transitions observed during Ice Age cycles. These reconstructions uncover intricate links between greenhouse gas levels, orbital forcing, and climate responses, encouraging model developers to include more detailed representations of these relationships. At the same time, greater computational power now makes it possible to simulate Earth's climate at much finer spatial and temporal resolutions, capturing small-scale processes such as cloud dynamics, ocean eddies, and permafrost feedbacks. These details are vital because they can either amplify or suppress broader climate signals, shaping long-term outcomes. Integrating dynamic ice sheet models into comprehensive climate systems further improves understanding of how changes in ice mass drive sea level rise and regional climate effects, resulting in a more cohesive perspective. Moreover, continued research into Earth's biogeochemical cycles, including carbon and nitrogen movements, has supported the creation of models that more faithfully represent how biological processes and human activity have influenced atmospheric composition over thousands of years. Bringing these processes together helps scientists forecast how future emissions and changes in land use may interact with natural climate variability. The validation of models has also been strengthened through international initiatives that build extensive climate archives and run collaborative simulation experiments. These shared platforms allow researchers around the world to evaluate models under a wide range of climate scenarios, encouraging steady improvements in accuracy, reliability, and robustness. As knowledge of Earth's climate feedback mechanisms grows, models become more adept at representing the delicate interplay of forces that drive long-term change. Within this evolving scientific landscape, cooperation among climate scientists, geologists, ecologists, and policymakers is crucial. Their combined efforts ensure that models stay anchored in empirical evidence, enhancing our capacity to anticipate future changes in Earth's climate system with greater clarity and confidence. International cooperation functions as a powerful driver of progress in Ice Age and climate research, bringing together experts from different fields and nations to piece together Earth's frozen history. The complexity of Ice Age processes encompassing glacial movement, paleoclimate reconstruction, and shifts in ancient ecosystems requires a breadth of expertise and data sharing beyond the reach of any single institution or country. Collaborative initiatives make it possible to combine resources supporting large-scale undertakings such as deep ice core drilling, the development of global climate models, and the detailed mapping of ancient environments at unprecedented levels of resolution. Through joint programs such as the European Project for Ice Coring in Antarctica EPICA and the International Ocean Discovery Program, IODP scientists can coordinate data collection and analysis, building a more integrated picture of climate variability over millions of years. These partnerships also encourage the standardization of research methods, ensuring that results can be compared and combined across regions and disciplines. The integration of archaeological, geological, and climatological data from multiple countries improves the accuracy of reconstructions, revealing patterns of human migration, volcanic events, and environmental change throughout the Ice Age. In addition, international collaboration accelerates the global sharing of discoveries, promoting dialogue and innovation across the scientific community. Many of these efforts include training programs that strengthen research capacity in less developed regions, expanding the scope of inquiry and ensuring that a diversity of perspectives shapes scientific understanding. Such cooperation is equally important for addressing present-day climate challenges, as insights gained from past climate variability help inform projections of future change. These shared endeavors extend beyond pure research, nurturing a collective sense of responsibility for Earth's history and environment as scientists, policymakers, and educators collaborate through global networks. Together, they establish a foundation for informed decision-making that aligns scientific knowledge with societal priorities. By uniting around the shared objective of understanding our planet's glacial past, international collaborations not only expand knowledge, but also reinforce a global commitment to the sustainable care of Earth's climate and landscapes. Public awareness and education surrounding Ice Age science hold significant potential to shape policy and conservation efforts in meaningful ways. When people understand the complexities of glacial processes, the record of Earth's climate fluctuations, and the fragile balance that maintains permafrost and ice sheet stability, they are better equipped to take part in developing sustainable solutions. Learning how past climate changes transformed landscapes and affected ecosystems highlights the need to protect these vulnerable regions for generations to come. Educating the public about the role glaciers and permafrost play in regulating the global climate can inspire a stronger sense of stewardship. For instance, understanding that thawing permafrost releases stored greenhouse gases such as methane helps illustrate feedback loops that can intensify climate change. When individuals grasp these concepts, they are more inclined to support policies focused on reducing emissions, conserving critical habitats, and investing in scientific research. Increased knowledge also helps counter misconceptions, encouraging informed discussion on topics such as geoengineering or resource extraction in glacial environments. Clear and effective communication of science can empower communities living near ice-rich landscapes by highlighting the importance of sustainable land management, resilient infrastructure, and adaptive strategies. In areas particularly vulnerable to permafrost thaw, educational initiatives can promote practices that limit environmental damage and protect essential infrastructure. Moreover, public participation through citizen science efforts, such as tracking glacier retreat or monitoring changes in permafrost temperatures, can produce valuable datasets while nurturing a shared sense of responsibility. The impact of a well-informed public also reaches policymakers who often depend on societal support to introduce and implement legislation. When scientific understanding of Ice Age-related phenomena is widespread, decision-makers are more likely to prioritize climate resilience, allocate funding for conservation, and support international collaboration aimed at protecting Arctic regions. In the long run, fostering a scientifically literate society creates a ripple effect that drives innovation, strengthens resilience, and promotes global action to confront the urgent challenges facing Earth's glacial and permafrost environments during a period of rapid climate change. As global temperatures continue their upward trend, the consequences for Earth's glaciers and permafrost zones grow increasingly significant. These frozen reservoirs act as critical indicators of climate stability, and their transformation carries far-reaching implications for the planet's future. Rising temperatures threaten to speed up. Glacier melt across the world, contributing to sea level rise on a scale capable of reshaping coastlines and displacing human populations. The disappearance of glaciers also reduces freshwater availability for millions of people, affecting agriculture, drinking water supplies, and ecosystems that rely on seasonal meltwater. Permafrost regions, which span vast polar and subpolar landscapes, are especially at risk. As warming progresses, permafrost begins to thaw, releasing large amounts of stored organic material. Its breakdown emits greenhouse gases such as methane and carbon dioxide, powerful contributors to further warming. This feedback loop has the potential to intensify global climate change, complicating efforts to predict and manage future conditions. Thawing permafrost also destabilizes ground surfaces, leading to erosion and damage to infrastructure, with serious consequences for indigenous communities and local economies. The destabilization of these frozen areas carries ecological impacts, as well as retreating ice alters habitats for specialized plants and animals, threatening biodiversity and shifting migration patterns. In some instances, newly exposed terrain becomes susceptible to erosion or invasion by non-native species, disrupting established ecosystems. In addition, the loss of reflective ice surfaces allows darker land and water to absorb more heat, accelerating both regional and global warming. Understanding how these changes may unfold is essential for developing effective adaptation strategies. Progress in remote sensing technologies and climate modeling enables scientists to better estimate the rate of glacier loss and permafrost degradation. These findings guide policy choices and reinforce the urgency of reducing greenhouse gas emissions to prevent irreversible environmental damage. As evidence continues to accumulate, the need to understand the intricate relationship between climate change and Earth's frozen regions becomes increasingly pressing, highlighting their role as both indicators and drivers of planetary health. Looking forward, Continued research is expected to deepen our understanding of these processes, uncovering details that could transform how we view Earth's climatic past and future. As research advances and new technologies emerge, our understanding of past ice ages continues to expand, revealing that future discoveries may fundamentally alter our perception of Earth's climate history and its direction. Improved paleoclimate indicators, including detailed ice core studies, sediment archives, and innovative isotopic methods, promise to sharpen timelines and clarify the forces behind abrupt climate transitions. For example, identifying previously unrecognized episodes of volcanic or solar activity could shed light on their influence in initiating or ending glacial phases, either challenging or reinforcing existing models that focus on orbital variations and greenhouse gas feedbacks. New approaches to analyzing ancient DNA from plants and animals may also transform our understanding of ecological resilience and extinction during glacial cycles. The discovery of new species or genetic information from long-extinct organisms could reveal adaptive strategies that were previously unknown, offering clues about how ecosystems responded to rapid climate shifts. This knowledge may help predict how modern species might adapt or struggle to adapt under current climate pressures. Advances in climate modeling, particularly those that integrate complex interactions among the atmosphere, oceans, biosphere and cryosphere, are likely to yield more precise reconstructions of past climates. Such enhanced models may uncover feedback mechanisms not previously recognized, including the roles of subglacial lakes or permafrost dynamics, which could have been critical during past climatic transitions. Acknowledging these influences has the potential to reshape how we view the stability of today's ice sheets and the likelihood of rapid ice loss in the years ahead. Moreover, as advancing drilling initiatives and increasingly sophisticated remote sensing technologies expand access to geological records, researchers may uncover previously unexplored areas that preserve vital evidence of regional climate variation and ice sheet dynamics. Such discoveries could question long-standing assumptions about the uniform nature of glacial cycles and instead expose a far more intricate mosaic-like history of Earth's ice ages. In the long run, ongoing research will strengthen our understanding of the complex network of forces that govern Earth's climate, providing both important warnings drawn from the past and practical insight for adapting to an uncertain future. Knowledge gained in this way will play a crucial role in shaping climate policy, guiding conservation strategies, and enriching our overall comprehension of Earth's ever-changing systems.